Welcome to a deep dive, folks. We're going deep into some math today.
Pretty intense math, yeah.
Dissipative measure-valued solutions and weak, strong uniqueness for the Euler alignment system. Have you seen this one?
Oh yeah, I've definitely come across this paper. It's a fascinating read, especially if you're into partial differential equations and collective behavior.
And that's us, right?
That is definitely us.
So Euler alignment system, that's all about how groups behave. I'm thinking, like flocks of birds, or how fish, like schools of fish, move together.
Exactly. That's the core idea. The Euler alignment system, as they've laid out in equation 1.1, it gives us this mathematical way to actually model these kinds of collective movements.
Equation 1.1. Yeah, it looks a little intimidating, if I'm being honest. Can we break it down a bit? What are we actually looking at here?
Sure, let's dissect it. We've got R-then that's representing the density of the group. So like how closely packed those birds are in a flock.
Okay, makes sense.
Then we have E, that's for the velocity, so the direction and speed of their movement. And then there's P, which is the pressure. Now, the thing about this pressure is that it's a function of the density. So the equation basically captures how these three things, density, velocity, and pressure, all interact and affect how the group moves.
So the pressure, the P, it changes depending on how dense the group is. Why is that?
Well, think about it this way. When a flock gets more dense, the birds are closer together, right?
Oh, right, yeah.
So that creates a kind of pressure, like they're all squeezed in. And that pressure then affects how they move. Like they'll adjust their velocity to avoid bumping into each other or to keep a certain spacing.
Ah, so it's like the denser they get, the more pressure they feel. And that makes them adjust how they're moving. It's all connected.
Yeah, exactly. It's this dynamic interplay between all these variables.
Now, there's this term in equation 1.2, the commutator Lu. What's that all about? What's it doing in this equation?
Well, that commutator is a key player. It's bringing in the concept of dissipation into the system.
Dissipation. Like they're losing energy over time.
Exactly. Think of a pendulum. It eventually slows down and stops because of friction, right? That's dissipation. And in our flock, it could be things like air resistance or the birds just using up their own energy. And this commutator, especially with its connection to the fractional Laplacian, it captures that energy loss mathematically.
So it's like bringing the real-world physics of flocking into the equation.
Precisely. It's acknowledging that these systems aren't perfect. They lose energy as they move and interact.
Now, the paper mentions that actually proving global well-posedness for this Euler alignment system, it's kind of a tough nut to crack. Why is that?
Yeah, it's a challenge. Proving global well-posedness basically means showing that a solution exists for all times and that it behaves in a way that makes sense. It doesn't just explode or become nonsensical.
Right.
And the Euler alignment system, it's pretty complex. Those non-local interactions, that commutator and the pressure effects, it's hard to be absolutely sure the solution will always be, well, nice.
So it's like we're trying to predict exactly how a flock of birds will move over a long period, but with all those interactions and external things happening, it's really hard to be sure, right?
That's a good way to put it. It gets very messy and unpredictable.
So then the paper brings up measure-valued solutions. What are those, and why do we even need them for systems like this?
Right, so sometimes those traditional solutions, what we call weak solutions, they just don't cut it for these complex systems. It might not even exist, or maybe there isn't just one unique solution. So we need something more, and that's where these measure-valued solutions come in.
They're like our backup plan.
More like a whole new toolkit. They give us a way to look at the average or statistical behavior of the system instead of trying to find the exact state at every single point in time and space.
Okay, so instead of getting bogged down in the details of each bird, we're looking at the flock as a whole.
Exactly. And that can be super helpful when you're dealing with a system as complex as a flock of birds. Imagine trying to track the precise flight path of every single bird. Exactly. It's way too much. But if you look at the flock as a whole, you can ask questions like, what's the average density in a certain area? Or what's the average velocity? You can get some really valuable insights that way.
So it's like we're zooming out and looking at the big picture instead of getting lost in the weeds?
Exactly. And that's where these measure-valued solutions shine. They let us see the forest for the trees, you could say.
Okay, I like that.
Yeah.
But how do they work? What's the math behind all of this?
They use something called Young measures. These are mathematical tools that can capture the probability distribution of values within a system. So instead of saying the velocity at this point is exactly this, we're saying there's a certain probability of the velocity being within this range.
So it's more like We're embracing the uncertainty. We're saying we don't know exactly where each bird is going, but we can figure out the probabilities.
Precisely. It's a much more flexible way to approach these complex systems where we can't have complete information all the time.
Now, the paper mentions this binary tensor Young measure in definition 2.2. What's so special about that kind?
Right. A standard Young measure looks at the distribution of values at one single point. But the binary tensor Young measure goes further. It captures the distribution at 2 points at the same time.
So it's like we're not just looking at individual birds anymore, but also at how they relate to each other.
Exactly. It's all about those relationships and interactions. And that's crucial for the Euler alignment system because of that non-local interaction term, the commutator. It involves comparing velocities at different points in the flock.
So it's like we need a tool that can see the connections between birds, not just the birds themselves. And the binary tensor Young measure is that tool.
You got it. It lets us analyze how those velocities at different points in the flock are correlated or how they influence each other. It's a really powerful way to understand how the flock moves as a whole.
Okay, this is all starting to make sense. But that definition of a dissipative measure-valued solution, definition 2.3, it's pretty intense. It feels like a lot to unpack.
It is, yeah. There are quite a few components to it, but basically it's laying out the criteria that a solution has to meet to be considered valid for this system.
Okay, so what's the first thing we need to check off the list?
Well, it needs to be representable by a Young measure. That's kind of the foundation. Capturing that probability distribution of density and velocity.
Okay, that makes sense, given what we've talked about. What's next?
Then there's something called the L-boundedness condition in equation 2.5.
L-infinity boundedness. That sounds a little intimidating.
It's not too bad, really. What it means is that the density and momentum of the system can't just blow up to infinity. They have to stay within certain bounds.
Okay, so it's another one of those constraints that keeps the solution grounded in reality. Like, birds can't suddenly become infinitely dense or move at warp speed.
Exactly. It's making sure the math reflects the physical limitations of the real world.
Makes sense. What else do we need to consider?
Well, there's this thing called the dissipation defect. It sounds a little ominous, but it's really just a way to account for the energy that's lost in the system due to things like friction and air resistance. Remember how we talked about how systems lose energy over time?
Right, like the pendulum slowing down.
Exactly. The dissipation defect is how we keep track of that lost energy mathematically.
Okay, that makes sense. What about this energy inequality in equation 2.0?
That's a fundamental concept in physics, and it applies here too. It basically states that the total energy of the system can never increase over time. It can only stay the same or decrease because of that dissipation we talked about.
So energy can't just magically appear out of nowhere. It has to come from somewhere and can be lost along the way.
You got it. It's all about conserving energy.
All right, then we have these compatibility conditions in equation 2.11. What are those all about?
Those are really important because they connect the world of measure-valued solutions to the world of smooth solutions. You know, the kind of solutions we usually think about in calculus. The compatibility conditions make sure that if a smooth solution exists, it'll agree with the measure-valued solution. It's like making sure they're telling the same story about the system.
So it's like a consistency check. We want to make sure these two different types of solutions are on the same page.
Exactly. We need both frameworks, the measure-valued and the smooth, to give us a consistent picture of what's going on.
Right. And what about the support of conditions in equations 2.12 and 2.12?
These conditions place some limits on the density and velocity, ensuring they stay within realistic bounds. So the density has to stay positive, you can't have a flock with negative birds, and the velocity can't become infinite, no birds moving at the speed of light.
Okay, so it's back to that idea of keeping the math grounded in the real world. No crazy, impossible scenarios.
Exactly. We want our solutions to make sense physically as well as mathematically.
And remark 2.2 mentions that because of all these conditions, the velocity is bounded in L2. Is that significant?
It is. It's a bit technical, but basically the L2 bound on the velocity means that the kinetic energy of the system, which is connected to how fast things are moving, is also controlled. So the flock can't just gain an unlimited amount of kinetic energy. Things have to stay within reasonable limits.
Got it. So another safeguard against things going haywire.
Precisely. We want our solutions to be physically plausible, and that means keeping the energy under control.
This definition is quite a mouthful. It's good we broke it down.
It is, but each part is crucial for ensuring that we're working with a solution that's both mathematically rigorous, and actually makes sense in the real world.
Okay, so we've laid the groundwork for understanding these dissipative measure-valued solutions. Now, on to the main results of the paper.
Sounds good. Let's see what these solutions can do.
Okay, so theorem 2.1, that's all about convergence, right? Like these approximate solutions actually converging to a real, dissipative measure-valued solution. Pretty important
Well,
stuff.
absolutely. This is where the authors really start to build things up. They show us how we can actually get to these measure-valued solutions by taking a limit of a sequence of these approximate solutions.
Right, so we're sort of working our way up to the real deal. But how do they even create these approximate solutions in the first place? What makes them approximate?
Good question. So these approximate solutions, they're actually solutions to a slightly modified version of the Euler alignment system. The authors add in this extra term, a viscosity term. You can see it in equation 2.1.
Viscosity. Isn't like how thick a fluid is or how much it resists flowing? What does that have to do with bird flocks?
You're thinking right. So imagine it like this. The viscosity term, it kind of smooths out those solutions, makes them a bit easier to handle mathematically. It's like adding a bit of give to the system. The original Euler alignment system, it can be a bit sharp in its changes, but the viscosity kind of rounds off those edges.
Okay, so it's like we're taming the system a bit, making it more manageable so we can actually analyze it.
Precisely. Those viscous solutions, they're more well-behaved, and that makes it a lot easier for us to study them and see how they change over time.
All right, that makes sense. Now, in the proof, they also assume that there's this uniform lower bound on the densities, that pro thingy. Why is that important?
That's a really crucial point. So that uniform lower bound on the densities, basically what it's saying is that the density of our flock, it never actually drops all the way down to zero.
So there are always at least some birds, right? They can't just vanish.
Exactly. You can't have a flock with no birds in it. And mathematically, this assumption, it prevents us from running into some weird situations where the density could, theoretically go to zero. That could create some nasty singularities and make the analysis a whole lot harder.
Got it. So it's like another one of those safeguards, making sure the math we're doing actually reflects what we'd expect to see in a real flock of birds.
That's it. We're keeping it grounded in reality.
So you've got these nice, well-behaved, viscous solutions. What happens next? Like, how do we get from these approximations to an actual measure-valued solution?
Well, the next step is to see what happens as we gradually make that viscosity smaller and smaller. We let that, the viscosity parameter approach zero, and this is where the idea of weak limits comes in.
Weak limits. I remember vaguely something about those from way back in my analysis classes. Something about, how sequences of functions can behave, right?
Yeah, you're on the right track. So weak limits, they give us a way to talk about convergence, even when those functions themselves might not converge in the usual way. Sometimes they might oscillate a lot, or maybe they have some jumps or discontinuities.
So even if the solutions are a little jumpy or all over the place, we can still kind of figure out their overall behavior using these weak limits.
That's the idea. It's a more flexible way to deal with convergence. And in the paper, they use some pretty powerful tools to identify these weak limits. They have the energy estimate in equation 3.1, that uniform lower bound on the densities that we talked about, and then some big guns like the Banach-Aloglu theorem and Young measure compactness.
Okay, those last two sound pretty intense. I'm going to trust you on those. But what are those theorems and estimates actually doing for us? What's their role in all of this?
They're kind of like the scaffolding for this whole convergence process. They guarantee that as we reduce that viscosity, our solutions, they don't just go crazy. They stay within certain bounds, and we can actually extract convergence subsequences.
So it's like we're herding those solutions, keeping them in line so we can analyze them properly.
Haha, that's a great way to put it. We need to have some control over how those solutions behave, and these mathematical tools give us that control.
Now, I noticed the paper talks a lot about identifying that non-local term in the limit. Why is that such a big deal?
Yes, that non-local term. Remember, that's the one with the commutator, the LAU. And that term is capturing those long-range interactions between the birds and the flock. It's like the communication channel between them.
So it's not just about where each individual bird is going. It's also about how they're all coordinating with each other across the whole flock, right?
You got it. And as we reduce that viscosity, getting closer to the true Euler alignment system, we need to make absolutely sure that this crucial part of the system's behavior is still being reflected in that measure-valued solution.
Okay, I can see how that could be tricky. How do they make sure that non-local term is behaving correctly in the limit?
Right. So they break it down into 3 different parts: Kel and all, Keefe and Keefe, each one representing interactions at different distance scales.
So it's like we're dividing the flock into groups based on how far apart the birds are, and then looking at how they're interacting within each group.
That's a great way to visualize it. By breaking it down like that, the authors can really get a handle on how that non-local term is behaving as the viscosity goes to zero. They use some tools like Holder's inequality, Lebesgue's dominated convergence theorem, and those energy bounds we talked about earlier to ensure that each part is converging properly.
Sounds like a lot of moving parts to keep track of.
It is. And remember that binary tensor Young measure we talked about? That's really important here too. It helps the authors capture those pairwise interactions between birds at different points in the flock, those interactions that the non-local term is all about. And it ensures that those interactions are still accurately represented even as the viscosity goes to zero.
So it's like a special lens that lets us see exactly how those interactions are changing as the system evolves, even at these tiny scales.
Exactly. That's the power of the binary tensor Young measure. It gives us the resolution we need to understand these subtle interactions.
Okay, so we've dealt with those approximate solutions converging, and we've got that tricky non-local term under control. What else is there to worry about?
Well, there are two key pieces left. The energy inequality and the compatibility condition. Remember those. They're part of the definition of what makes a dissipative measure-valued solution valid, so we need to be absolutely sure that they still hold true even as we take that limit and the viscosity goes to zero.
Right, so we're building up our case piece by piece, showing that this final solution we get actually meets all the requirements we set out in that definition.
Precisely. It's like a quality control check, making sure everything is in order.
Yeah.
So the energy inequality, that's equation 2-point Barrow, remember, it reflects the fact that energy is being lost in the system over time because of dissipation. And the proof shows that this inequality, it doesn't break down as we take the limit. It's still valid.
So even though we're changing the system by getting rid of that viscosity, the basic energy dynamics are still working the way they should.
Exactly. We're not messing with the core physics of the problem.
Okay, what about that compatibility condition? How do we handle that?
Right. So that condition, equation 2.11, it basically ensures that if we happen to have a smooth solution lying around, it'll agree with our measure-valued solution. They'll be telling the same story. And to prove this, the authors use some really clever inequalities and leverage the properties of the fractional Laplacian. They basically show that the difference between the measure-valued solution and any potential smooth solution, it's nicely bounded, it doesn't blow up or do anything crazy.
So it's like we're making sure that if there is a smooth solution out there, it's not going to veer off wildly from the path laid out by the measure-valued solution. They have to stay somewhat in sync.
Exactly. The compatibility condition acts like a tether, keeping those two types of solutions connected.
This is so intricate. There are so many details to keep track of.
It is. It's really impressive how the authors have meticulously constructed this logical framework to demonstrate their results.
And I bet these results have implications beyond just bird flocks, right? I mean, this kind of math, it feels like it could apply to all sorts of things.
Oh, absolutely. The techniques and the ideas they've developed here, they have the potential to be applied to tons of different phenomena. Think about traffic flow, or how crowds move, or even how things work in financial markets.
Wow, so we're talking about a mathematical framework that could help us understand some really complex systems?
Exactly. That's the beauty of it. This kind of mathematical modeling, it allows us to see the patterns and the underlying principles behind things that might seem totally random or chaotic, and that can give us insights that could lead to better predictions, maybe even new ways to control these systems.
Okay, before we get too carried away, let's finish up with this proof of theorem 2.1. We've covered the convergence, that non-local term, the energy inequality, and the compatibility condition. What's the last piece?
The final step is to take a look at the support of that binary tensor Young measure, the ints. Remember, the support of a measure, it tells us where the action is happening, the values that actually have a chance of occurring.
So if we're thinking about our flock, it's like figuring out where we're actually likely to find birds, or what kind of speeds they'll be flying at, right?
Yeah, that's a good way to think about it. And in the proof, they show that the support of that measure, it's actually restricted to a specific set. They call it at XX, XY2. And that restriction makes sure that the density stays positive, no negative birds allowed, and it also keeps the velocity finite. So no birds exceeding the speed of light. It's all consistent with those physical constraints we've been talking about.
So it's like another one of those reality checks, making sure that the solution is behaving in a way that actually make sense in the real world?
Precisely. And by showing that all these pieces fit together, the convergence, the non-local term, the energy inequality, the compatibility condition, and the support of that measure, the authors have rigorously shown that a dissipative measure-valued solution, as they defined it, actually exists.
Wow, it's amazing how they put it all together. I'm starting to really appreciate how these measure-valued solutions are built and why they're so important for understanding these kinds of systems.
It's been quite a journey, hasn't it? But I think it's really worth it to see how powerful and elegant this mathematical framework is.
I agree. It's incredible how these abstract mathematical ideas can be used to model and predict real-world behavior, like how flocks of birds move. This paper has definitely given me a whole new perspective on the depth and beauty of mathematics.
Absolutely. It shows you how much careful thought and reasoning goes into these proofs and how much we can learn from them.
Now, on to the grand finale. I'm really curious to see how that weak, strong uniqueness principle plays out in the proof of Theorem 2.2. That feels like the culmination of all this work we've been discussing.
Oh, yes, you're in for a treat. Theorem 2.2, that's where the true elegance of this whole framework really shines through.
Okay, Theorem 2.2, weak, strong uniqueness. Bring it on. This is what we've been waiting for.
It's a really neat result. It's saying that if we've got a smooth solution, that's the only solution we need to worry about, even with all these measure-valued solutions floating around.
I mean, less is more, right? But how do we prove something like that? It sounds pretty deep.
The trick is this thing called the relative energy inequality. You can see it in the paper. They call it MEESUR. It's basically a way to measure how different a measure-valued solution is from a smooth solution.
So it's like we're putting them head to head, seeing which one comes out on top.
Yeah, kind of. We have our measure-valued solution with its Young measure, density S, and velocity U. Then we bring in a smooth solution with density R and velocity U. This relative energy, it tells us how much their energies and momenta differ.
Looking at that equation, it's a lot. What are we comparing exactly?
Okay, let's break it down. We're using integrals over space to compare their kinetic energies, which depend on the velocities U and U, and also their potential energies, which come from the pressure. The pressure potential, PS, that's a big part of it too.
So it's like a full energy audit, seeing where these two solutions match up and where they diverge.
Exactly. Any difference between them will show up in this relative energy. And the goal is to prove that if they start from the same initial data, meaning they're identical at the beginning, then this relative energy stays zero forever. If they start the same and never diverge, they're the same solution.
Makes sense. But how do we actually get there? That inequality is pretty intimidating.
It takes some work. First, we use those equations of continuity and momentum, the ones that both solutions have to satisfy. For the measure-valued solution, those are equations 2.7 and 2.9. For the smooth one, it's 4.6 and 4.8.
So we're using everything we know about how they evolve.
Exactly. We plug those equations into the relative energy inequality, and things start to get a little neater.
I bet those non-local terms show up again. Those integrals over pairs of points, all those interactions.
Of course. And this is where the binary tensor Young measure really shines. Its symmetry and consistency, remember remark 2.1, we use those properties to handle those non-local terms.
The right tool for the job.
You got it. Now, the proof also uses Gronwall's lemma. Remember that one?
Vaguely. It's something about bounding how functions grow, right?
Yeah. It basically says that if a function starts at 0 and its growth is controlled in a specific way, it stays 0 forever. And that's exactly what we need to show for our relative energy.
So we're putting a leash on it, keeping it from growing out of control and messing up our proof.
Exactly. We're showing that its growth is bounded by 0, which means it has to stay put.
It's all coming together. We're using those equations, the Young measure properties, Gronwall's lemma, all to show that the relative energy stays 0 if the solutions start the same.
And that means they're the same solution. So if we find a smooth solution, we're done. We don't need to worry about any other complicated measure-valued solutions.
It's pretty amazing how much simplification we get from this weak, strong uniqueness.
It is. It makes studying these systems a lot easier.
Wow, we've really gone deep today. From birds flocking to these incredibly detailed mathematical proofs.
It's been a fantastic journey. This paper really showcases how powerful math can be in helping us understand complex systems.
I totally agree. And who knows what other amazing mathematical tools are out there, just waiting to be discovered and applied to new problems. Thanks for joining us for this deep dive into the Euler alignment system and measure-valued solutions. We hope you learned a lot and maybe even got inspired to explore some of these ideas further. Until next time.
Welcome to our deep dive into the world of mathematics and collective behavior. Imagine like a flock of birds just moving in unison.
Yeah.
Or, a school of fish just darting around together.
It's fascinating.
How do they do it?
Yeah, it is. It's a fascinating area.
That's what we're going to explore.
Where math meets nature.
Today, specifically through the lens of the Euler alignment system.
And we will be unpacking a research paper titled Dissipative Measure-Valued Solutions and Weak-Strong Uniqueness for the Euler Alignment System.
Sounds a bit daunting.
By Chaudhary, Koley, and Wiedemann.
That's why you're here, to help us navigate the complexities.
Absolutely.
Our mission is to understand how mathematicians are tackling this system, particularly when dealing with, generic initial data.
Exactly.
It's about going beyond those idealized scenarios.
Think of it like this.
And embracing the messiness of real-world conditions.
If you were trying to predict the movement of a flock, you wouldn't know the exact position and velocity.
I'm starting to see the challenge here.
Of every bird at the start.
So how does the Euler alignment system attempt to model these swarms?
That's where generic initial data comes in.
Okay.
At its core
Right.
is a system of partial differential equations. And equation 1.1 is where it all begins. Let's break it down. You have rho, which represents density, U for velocity, P for pressure, and lu, which stands for the fractional Laplacian.
Fractional Laplacian. Now, that sounds intriguing.
Think of it as a way to describe how things spread or diffuse, like information or movement, propagating through the swarm.
Oh, okay.
It captures the non-local interaction.
So these equations are attempting to capture.
Meaning individuals aren't just responding to their immediate neighbors.
The intricate interactions within the swarm.
But also to those farther away.
How individuals respond to each other's movements, density changes, and those non-local effects.
Precisely.
Okay, so even with these intricate equations...
The challenge with the Euler alignment system.
Mathematicians are hitting a wall with traditional solution methods.
And this is where it gets really interesting. Is finding a global well-posedness. That means finding a solution.
So what's the alternative?
That exists and makes sense for all time. This becomes quite tricky. Especially with the pressure term involved.
That's where the concept of measure-valued solutions comes into play?
That's right. Instead of looking for solutions.
Instead of looking for solutions as functions, which can be very restrictive, we think of them as space-time parameterized probability measures. You're essentially shifting from a deterministic viewpoint to a probabilistic one.
You're absolutely right. That's exactly right.
Hold on, probabilities.
Yeah.
So we're saying we can't pinpoint the exact state of the system at every moment.
It's more about acknowledging that we might not have complete information. Imagine you're tracking the flock again. Instead of needing to know the precise location of every bird, you can describe the probability of finding a bird within a certain area.
So it's about embracing uncertainty.
It's like saying...
And working with the information we have. That makes sense.
I'm not sure exactly where each bird is, but I have a good idea.
Given the complexities of real-world scenarios. But why are these measure-valued solutions any easier to work with?
Of where they're likely to be. One of the main advantages is that they allow you to capture a broader class of solutions that may arise from approximate problems, which are more manageable mathematically. These approximate problems might incorporate things like viscosity terms.
That's a great way to put it. So we've got our approximate problems.
That smooth out the behavior of the solutions.
But how do we connect them to the original Euler alignment system?
It's like creating a simplified version.
That's where these young measures come in, right?
Have a system that still captures its essence. Exactly. Young measures are mathematical objects that allow us to describe the probability distribution of our solutions. They essentially provide a way to bridge the gap between our approximate solutions.
So I'm starting to see the pieces come together.
And the true solution of the Euler alignment system, think of them as a way to keep track of the uncertainty that we've introduced.
But how do young measures help us with that tricky non-local term we talked about earlier, the fractional Laplacian?
That's where things get even more interesting. The standard techniques for handling non-linear terms using young measures don't quite work for non-local terms. So we need a more specialized tool. The binary tensor young measure.
That's the ETT. XY from definition 2.2 in the paper. I'm ready to dive into the specifics.
A binary tensor Young measure is formed
Okay.
by taking the Young measure at a point in space and time,
Okay.
x and t, and multiplying it
Uh-huh.
by the Young measure at another point
So it's like looking at the correlations between the states of the system at different points.
at the same time.
Why is that crucial for the non-local term?
Instead of looking at the probability distribution at just one point,
Okay.
you're considering the joint probability distribution at 2 points simultaneously.
Remember, the fractional ablation describes how things spread through the swarm, those non-local interactions,
Right.
by using the binary tensor Young measure.
Remember, the fractional ablation
We can accurately capture the influence of the system's state at one point,
describes how things spread through the swarm.
on the state at another point, even when working with approximate solutions.
Those non-local interactions.
That makes sense. So the binary tensor Young measure is like a lens that lets us see the non-local connections,
By using the binary tensor Young measure,
even when we're working with a simplified version of the system.
we can accurately capture
Are there any other important properties of these binary tensor Young measures?
the influence of the system's state at one point on the state at another point,
Right.
even when working with approximate solutions.
Okay, so we have these powerful tools
Yes. Remark 2.1 highlights the symmetry
to handle the complexities of the Euler alignment system.
and consistency of these measures.
But how do we actually define a solution using this measure-valued approach?
This means that they behave in a way that aligns with our intuition about how the system should work.
Right.
For example, the symmetry property reflects the fact that the interaction between 2 points
Okay.
should be the same regardless of which point we consider first.
That's where definition 2.3 in the paper comes in.
And the consistency property ensures
It lays out the criteria for what constitutes a dissipative measure-valued solution for this system. It's like a checklist.
that the binary tensor Young measure reduces to the standard Young measure
To ensure our solution makes sense both mathematically and physically.
when the 2 points are the same.
Dissipative. Does that mean the system is losing energy?
Okay, so we have these powerful tools to handle the complexities of the Euler alignment system.
Okay.
But how do we actually define a solution
Right.
using this measure-valued approach?
So what are the conditions for a solution to be considered a dissipative measure-valued solution?
That's where definition 2.3 in the paper comes in.
Okay.
It lays out the criteria for what constitutes
Right.
a dissipative measure-valued solution for this system.
First,
It has to involve a Young measure.
to ensure our solution makes sense both mathematically and physically.
That probability distribution we've been discussing, it also needs to be bounded.
Yeah.
You can't have infinitely large densities or velocities in your swarm. Then there's the dissipation defect, which is a measure of how much energy might be lost in our approximate problem.
It can, but dissipative here
Okay.
is more about the system.
So far, so good. Are there other criteria for our dissipative measure-valued solutions?
Being realistically irreversible. Remember those approximate problems with viscosity terms?
Okay. That viscosity can lead to energy dissipation.
All right.
So what are the conditions for a solution to be considered a dissipative measure-valued solution?
Okay.
First, it has to involve a Young measure, that probability distribution we've been discussing.
Yeah.
It also needs to be bounded.
Right.
You can't have infinitely large densities
Okay.
or velocities in your swarm. Then there's the dissipation defect, which is a measure of how much energy might be lost in our approximate problem.
So are there other criteria for our dissipative measure-valued solutions?
Of course. We also need an equation of continuity,
Okay.
ensuring that the total mass of our swarm is conserved.
All right.
Then there's the momentum equation describing how the momentum of the swarm evolves.
These conditions sound like fundamental physical principles.
And an energy inequality setting a bound on the system's total energy.
Okay.
They are. And to add more rigor,
Right.
we have compatibility conditions that further restrict the behavior of our solutions.
Okay.
One of these,
Okay.
presented in equation 2.11,
So it's like a bridge between this new framework and the classical approaches.
ensures our measure-valued solutions agree with smooth classical solutions.
What about that support we mentioned earlier?
If they exist.
Right.
Right. We need to specify the support of the binary tensor Young measure,
Okay.
which means defining the range of possible densities and velocities our solutions can take. Equations 2.12 and 2.13 make sure the densities are always positive. You can't have negative birds in your flock.
Okay. It's all starting to click now. We have a clear definition of a dissipative measure-valued solution.
Okay.
Now, what are the key results of the paper?
There are two key theorems.
Okay.
First, Theorem 2.1 shows that, under certain conditions,
So we're not just simplifying for the sake of simplicity.
a family of solutions to the approximate viscous problem
It actually leads us to a real solution.
will converge to a dissipative measure-valued solution
Okay.
as we make the approximation increasingly precise.
So the regularized system refers to our original Euler alignment system,
Think of it as saying
but with an added viscosity term, right, to smooth things out, so to speak.
our simplified choreography actually leads us to a valid representation of
Right.
the original complex dance.
All right.
Exactly. The second theorem,
So if we happen to find a nice, smooth solution, our measure-valued solution won't contradict it.
Theorem 2.2,
It guarantees the two approaches are compatible.
establishes a weak, strong uniqueness principle.
This is amazing, but I'm curious, how do we prove these theorems?
It states that if you have both,
Oh.
a dissipative measure-valued solution
Right.
and a smooth classical solution starting from the same initial data,
That's where the real mathematical heavy lifting begins. To prove Theorem 2.1,
they'll be identical as long as the smooth solution exists.
we need to dive into the details of how those approximate solutions converge. It involves some powerful tools from functional analysis
So if we happen to find a nice, smooth solution,
and a meticulous analysis of the behavior of each term in our equation as the approximation gets more precise.
our measure-valued solution won't contradict it. It guarantees
What does that mean exactly?
the two approaches are compatible.
Okay.
Indeed, it demonstrates
Sure.
the robustness of this measure-valued approach.
It's a way of describing how the solutions behave as we make our approximation more and more precise.
Not only does it handle more realistic initial conditions,
Okay.
but it also agrees with the classical solutions
Right.
whenever they exist.
Okay.
This consistency is reassuring.
So it's like focusing on the choreography of the flock as a whole, even if individual birds are still making small adjustments.
And highlights the elegance of
Perfect.
this mathematical framework.
Now, thanks to the energy estimate
That's where the real mathematical heavy lifting begins.
and the uniform lower bound on densities,
To prove Theorem 2.1,
our solutions are well behaved,
we need to dive into the detail.
which means we can derive certain bounds on quantities like the density, momentum, and velocity.
Of how those approximate solutions converge.
You can see these bounds in equations 3.3 and 3.4.
It involves some powerful tools from functional analysis
With these bounds in place.
and a meticulous analysis of the behavior of each term in our equations as the approximation gets more precise.
We can use some heavy-duty mathematical tools like the Banach-Laglu theorem
Yeah.
and young measure compactness.
The proof starts by considering a family of viscous, dissipative, weak solutions.
These tools allow us to extract convergent subsequences from our family of solutions.
To the regularized system.
So we're using these sophisticated tools to extract meaningful information from our approximate solutions, even if they're not perfectly converging.
The regularized system refers to our original Euler alignment system,
I'm curious, though, what kind of convergence are we talking about here?
but with an added viscosity term, right?
Okay.
To smooth things out, so to speak.
Right.
Exactly. And this family of solutions is assumed
The convergence here is in the weak sense.
to satisfy an energy inequality, which essentially
On the-
sets a limit on the total energy of the system. This is equation 3.1 in the paper.
It's a specific type of convergence that's commonly used in the study of partial differential equations.
Also, we assume there's a positive constant that acts as a lower bound,
Okay.
the densities, meaning the swarm can't completely disappear.
All right.
This is captured in equation 3.2. With these assumptions in place,
Instead of requiring the solutions to converge pointwise,
we can start to analyze.
we only require them to converge when tested against smooth functions called test functions.
How these solutions behave.
Test functions. So it's like probing the solutions with specific mathematical instruments to see how they respond.
As we refine the approximation, what we are looking for
Okay.
are the weak limits of our solutions.
Right.
Weak limits.
And the key takeaway is that this weak convergence of our solutions to a Young measure
It's a way of describing how the solutions behave.
implies that quantities like density, momentum, and velocity also converge in a weak sense.
As we make our approximation more and more precise,
Okay, I'm starting to see the pattern here. We're meticulously building up our argument step by step.
even if they don't converge in the traditional sense.
Okay.
Think of it as capturing the overall trend
All right.
of the solutions, even if they might still be fluctuating a bit.
Now, while most of the terms in our equations converge in a relatively straightforward manner,
These fluctuations are often present in solutions to partial differential equations.
due to the bounds we've established and the properties of weak convergence, there's one term that requires a more delicate touch, the non-local term, involving the fractional Laplacian.
And the concept of weak limits provides a way to handle them.
Ah, there it is. The fractional Laplacian always seems to add a layer of complexity. How do we handle it?
So it's like focusing on the choreography of the flock as a whole,
Okay.
even if individual birds are still making small adjustments.
Okay.
Precisely. Now, thanks to the energy estimate and the uniform lower bound on densities,
Since the usual techniques with Young measures don't work directly, we need a more refined approach.
our solutions are well behaved, which means we can derive.
The key is to break down the non-local term into smaller, more manageable pieces and analyze each piece separately. You can see this detailed analysis from equation 3.5 to equation 3.17 in the paper.
Certain bounds on quantities like the density, momentum, and velocity.
Divide and conquer, I like it. So we break it down, analyze each piece, and then what?
You can see these bounds in equations 3.3 and 3.4.
Okay.
With these bounds in place,
All right.
we can use some heavy-duty mathematical tools like the Banach-Alaoglu theorem.
The payoff for this meticulous work is that we're able to identify the limit of the non-local term in terms of that binary tensor Young measure we discussed earlier. This is shown beautifully in equation 3.17.
And Young measure compactness, these tools allow us.
It's like solving a jigsaw puzzle. Each piece might seem insignificant on its own, but when they all come together, you see the bigger picture.
To extract convergent subsequences from our family of solutions, the magic here
I love that analogy. It's really starting to feel like all these pieces are fitting together.
is that these subsequences converge to a Young measure,
But now that we've handled the convergence of all the terms, what's next?
denoted as heat temp-tex.
Okay.
Even if the original solutions themselves
Right.
didn't converge in a traditional sense?
We need to ensure that our limiting solution, the one we've meticulously constructed,
You see this in the long list of convergence results right after equation 3.4.
also satisfies an energy inequality.
So we're using these sophisticated tools
Remember, those energy inequalities are like safeguards,
to extract meaningful information
ensuring our solution doesn't behave in a physically impossible way.
from our approximate solutions,
Equation 3.18 comes into play here,
even if they're not perfectly converging.
showing that the energy of the approximate solutions converges to a term involving the binary tensor Young measure. But there's an additional term, a measure denoted as IVAS,
I'm curious, though.
which captures any potential energy dissipation that might occur in the limit.
What kind of convergence are we talking about here?
So it's like acknowledging that some energy might leak out of the system
The convergence here
as our approximation becomes more precise.
is in the weak sense.
Is that where the dissipation defect comes in?
It's a specific type of convergence that's commonly used in the study of partial differential equations. Instead of requiring the solutions to converge pointwise, we only require them to converge when tested against smooth functions called test functions.
You got it.
Test functions.
The dissipation defect, denoted by D, is a measure of this potential energy leakage.
So it's like probing the solutions with specific mathematical instruments.
And we can prove that this dissipation defect controls the behavior of another measure, Rm,
To see how they respond.
which is related to the convergence of the momentum flux.
That's a great analogy.
This relationship is captured in equation 2.8. And the key takeaway is that this weak convergence, now we're getting closer to establishing that our limiting solution
Of our solutions to a Young measure,
is indeed a dissipative measure-valued solution.
implies that quantities like density, momentum, and velocity
What else do we need to show?
also converge in a weak sense.
Okay.
I'm starting to see the pattern here.
All right.
We're meticulously building up our argument step by step.
We need to prove the compatibility condition.
Exactly. And while most of the terms in our equations converge,
Remember, this condition ensures that our measure-valued solution agrees with the classical solutions if those classical solutions exist.
in a relatively straightforward manner due to the bounds we've established.
It's like a bridge between the worlds of traditional solutions and these more generalized measure-valued solutions. The compatibility condition is presented in equation 2.11. And to prove it, we need a technical result from functional analysis, the dominance of the fractional Laplacian semi-norm over the usual L2 norm. This is a powerful result, given in proposition 1.2 of reference 5, that allows us to control the behavior of the solutions.
And the properties of weak convergence, there's one term that requires a more delicate touch.
So we're bringing in even more mathematical machinery to solidify our argument.
The non-local term involving the fractional ablation.
Okay.
Ah, there it is.
Right.
The fractional ablation always seems to add a layer of complexity.
By carefully analyzing the terms in the compatibility condition,
How do we handle it?
using our weak convergence results and the properties of the fractional ablation,
Since the usual techniques with Young measures,
we can establish the desired inequality. You can see the details of this analysis from equation 3.19 to equation 3.24 in the paper.
don't work directly. We need a more refined approach.
Okay, we've handled the energy, the non-local term, and the compatibility condition. What's left?
The key is to break down the non-local term into smaller, more manageable pieces and analyze each piece separately.
Okay.
You can see this detailed analysis from equation 3.5 to equation 3.17 in the paper.
The final piece of the puzzle is the support of the binary tensor Young measure. Remember, this is all about specifying the range of possible values for our solutions. We need to show that the densities are always positive. Equations 3.25 and 3.26 confirm that. You can't have a swarm with negative density, right?
Divide and conquer.
Right. With that, we've met all the criteria to prove theorem 2.1.
I like it. So we break it down, analyze each piece, and then what?
It's been quite a journey, but we've shown that our approximate solutions actually converge to a dissipative, measure-valued solution as we refine the approximation.
The payoff for this meticulous work is that we're able to identify the limit of the non-local term in terms of that binary tensor Young measure we discussed earlier.
Right.
This is shown beautifully in equation 3.17. It's like solving a jigsaw puzzle. Each piece might seem insignificant on its own.
Precisely. Now, are you ready to tackle theorem 2.2, the weak-strong uniqueness principle?
But when they all come together,
Absolutely. But perhaps it's a good stopping point for part 1 of our deep dive.
you see the bigger picture. Okay.
I love that analogy. It's really starting to feel like all these pieces are fitting together.
We've covered the definition of a dissipative measure-valued solution and even begun to unravel the intricacies of Theorem 2.1's proof.
But now that we've handled the convergence,
Join us in part 2, where we'll delve into the fascinating proof of the Weierstrass uniqueness principle and explore its implications for understanding collective behavior.
of all the terms, what's next?
Welcome back to our deep dive into the Euler alignment system. We've laid out the groundwork, explored the challenges of traditional solution methods, and discovered the fascinating world of dissipative measure-valued solutions.
It has been quite an adventure, hasn't it?
Now we're about to tackle the proof of Theorem 2.2, the Weierstrass uniqueness principle. Are you ready to unravel this mathematical mystery?
Absolutely. The Weierstrass uniqueness principle is a cornerstone of this framework.
I'm all ears.
And its proof involves some elegant mathematical concepts. It's a testament to the power of abstract tools.
Where do we begin? To illuminate our understanding of real-world phenomena, the key to proving this principle lies in introducing a powerful tool called the relative energy functional.
So it's like a mathematical ruler for measuring the difference between solutions.
Yeah.
Why is this important for the Weierstrass uniqueness principle?
It allows us to compare two different solutions in this case, a measure-valued solution denoted by RD and a smooth classical solution denoted by RU, and quantify how far apart they are.
Okay.
Remember, the Weierstrass uniqueness principle aims to show that these two types of solutions,
All right.
measure-valued and classical,
Okay.
are identical if they start from the same initial data.
Right.
If we can demonstrate that the relative energy function between them
So how do we define this relative energy functional?
is 0, it implies they are indeed the same solution.
Okay.
The relative energy functional, denoted by MEV, is defined in equation 4.1 of the paper. It involves calculating the difference between the energies of the measure-valued solution and the smooth solution.
It sounds like we're accounting for all the potential discrepancies between the solutions. So what's the strategy for proving that this relative energy functional is actually 0?
Along with additional terms involving the pressure and the differences in densities and velocities between the two solutions, the heart of the proof lies in meticulously analyzing.
I'm guessing this is where equations 4.1 through 4.5 come into play.
How this relative energy functional evolves over time. Our goal is to show that it doesn't grow too rapidly. And ideally that it remains bounded.
What kind of manipulations are we talking about?
You're exactly right. Those equations involve a series of manipulations and calculations aimed at rewriting the relative energy functional
All right.
in a more convenient form, one that allows us to control its growth.
So we're strategically rearranging the equation, so to speak, to get a better grip on how it behaves. And what do we do once we have this more manageable form?
We leverage the equations of continuity and momentum, those fundamental principles governing the conservation of mass and momentum in the system,
Okay.
along with the properties of the Young measure and the pressure function.
Right.
This allows us to express the relative energy functional in a way that makes it easier to estimate its terms and control its behavior over time.
Gronwall's inequality. It's like a mathematical magic wand. But before we can wave that wand, we need to ensure that the derivative of the relative energy functional is indeed well-behaved.
This is where a powerful mathematical tool called Gronwall's inequality comes into play.
Okay.
Gronwall's inequality, a staple in the study of differential equations,
Right.
provides a way to bound the growth of a function if we can control its derivative and initial value.
Okay.
If we can show that the derivative of the relative energy functional...
Precisely. And that's where the heavy lifting comes in. Equations 4.6 through 4.38 in the paper detail. A meticulous process of estimating the various terms in our rewritten relative energy functional.
is bounded by some expression
It's a delicate dance involving careful analysis,
involving the relative energy functional itself.
leveraging the assumptions we've made about the smooth solution, R, in equation 2.15, and utilizing the properties of the measure-valued solution, D, and the fractional Laplacian.
Then Gronwall's inequality allows us to conclude
Okay.
that the relative energy functional remains bounded over time.
So it's a lot of intricate calculations, but with a clear goal to bound the growth of the relative energy functional.
Precisely. And that's where the heavy lifting comes in.
And if we can do that, Gronwall's inequality swoops in to save the day.
Equations 4.6 through 4.38 in the paper
Okay.
detail a meticulous process of estimating the various terms
All right.
in our rewritten relative energy functional. It's a delicate dance
Okay.
involving careful analysis.
That's incredible. We've shown that the distance between our measure-valued solution and the smooth solution is 0, meaning they must be the same.
Leveraging the assumptions we've made about the smooth solution
The weak, strong uniqueness principle is proven. What a journey.
in equation 2.15
Okay.
and utilizing the properties of the measure-valued solution, any, and the fractional Laplacian.
Indeed. It demonstrates the robustness of this measure-valued approach. Not only does it handle more realistic initial conditions,
And the culmination of this intricate estimation process
but it also agrees with the classical solutions whenever they exist.
is a crucial inequality presented in equation 4.38 that sets.
This consistency is reassuring and highlights the elegance of this mathematical framework.
An upper bound on the growth of the relative energy functional. This is the key that unlocks
Absolutely. But we're not done yet, right?
the power of Gronwall's inequality.
We've proven the existence of these dissipative, measure-valued solutions and established the weak, strong uniqueness principle. But what does it all mean? What are the implications of this research?
We apply Gronwall's inequality to this carefully crafted inequality,
Okay.
leading us to the beautiful conclusion that the relative energy functional
Right.
is, in fact, 0.
Okay.
That's incredible. We've shown that the distance between our measure-valued solution and the smooth solution
The implications are far-reaching. For starters, this framework provides a powerful tool
is 0, meaning they must be the same.
for tackling problems involving collective behavior in various fields.
The weak, strong uniqueness principle is proven. What a journey.
From understanding the movement of bird flocks and fish schools in biology to designing swarms of robots in engineering, the Euler alignment system, with its newly established measure-valued solution framework, offers a mathematically rigorous way to model and analyze these complex systems.
Indeed, it demonstrates the robustness
I can see how this could be applied in so many areas.
of this measure-valued approach.
It's like we've uncovered a new language for describing the intricate dance of nature.
Not only does it handle more realistic initial conditions,
Okay.
but it also agrees with the classical solutions whenever they exist. This consistency is reassuring
All right.
and highlights the elegance of this mathematical framework.
Precisely. And this new language allows us to go beyond simply observing these phenomena. We can start to make predictions, understand the underlying mechanisms.
The implications are far-reaching. For starters,
and even design systems that leverage the principles of collective behavior.
this framework provides a powerful tool for tackling problems involving collective behavior.
Think about the potential for developing more efficient traffic flow models, understanding the spread of epidemics, or even controlling the movement of autonomous vehicles.
In various fields.
The possibilities seem endless. But before we get carried away by the potential applications, I'm curious about something you mentioned earlier, the use of measure-valued solutions. It seems like a radical departure from traditional solution methods. Can you elaborate on why this approach is so significant?
From understanding the movement of bird flocks and fish schools in biology to designing swarms of robots in engineering, the Euler alignment system, with its newly established measure-valued solution framework, offers a mathematically rigorous way to model and analyze these complex systems.
You're right. It represents a fundamental shift
Exactly.
in how we think about solutions to partial differential equations.
Precisely. And this new language allows us to go beyond simply observing.
Especially those describing complex, nonlinear phenomena like fluid flow, shock waves, and of course, collective behavior.
These phenomena.
Traditional methods often struggle with these types of equations,
We can start to make predictions, understand the underlying mechanisms.
either failing to find solutions or producing solutions that are not unique or physically meaningful. The beauty of measure-valued solutions lies in their ability to embrace uncertainty and capture a wider range of solution behaviors.
And even design systems that leverage the principles of collective behavior. Think about the potential for developing.
So it's like saying we're acknowledging that perfect knowledge isn't always attainable, and that sometimes it's more meaningful to work with probabilities and ranges of possible outcomes.
More efficient traffic flow models.
Okay.
Understanding the spread of epidemics, or even controlling the movement of autonomous vehicles.
That's a wonderful analogy. And the key is that this probabilistic description, captured by the Young measures we discussed earlier, still allows us to extract meaningful information about the system. We can calculate quantities like the average density or velocity of the flock, the probability of the flock reaching a certain area, and other statistically relevant properties.
The possibilities seem endless.
It's amazing how these seemingly abstract mathematical concepts
You're right.
can provide such practical and insightful tools for understanding real-world phenomena. I'm even more curious now about how these measure-valued solutions are actually found. Is there a standard method or algorithm?
It represents a fundamental shift in how we think about solutions
Okay.
to partial differential equations, especially those describing complex, non-linear phenomena
All right.
like fluid flow, shock waves, and of course, collective behavior.
That's a great question.
Traditional methods often struggle with these types of equations.
Unfortunately, there isn't a single universal method for finding measure-valued solutions.
Either failing to find solutions or producing solutions
The approach often involves constructing approximate solutions that converge
that are not unique or physically meaningful.
to a measure-valued solution in a specific mathematical sense. These approximate solutions might involve techniques like adding viscosity terms to the equations, discretizing the equations on a grid, or utilizing sophisticated numerical methods.
The beauty of measure-valued solutions lies in their ability to embrace uncertainty and capture a wider range of solution behaviors.
So it's like simplifying the choreography in a controlled way so that we can handle it mathematically, but then making sure that our simplified version still captures the essence of the original dance.
By working with probability distributions instead of exact values, we can handle situations where complete information is simply not available, or where the solutions exhibit oscillations or concentrations that make traditional methods break down.
Precisely. And that's why research in this area is so vibrant and exciting. There are many open questions and challenges related to finding efficient and practical methods for computing these measure-valued solutions. The computational cost can be quite high, especially for large-scale systems. Developing new algorithms and computational techniques is a crucial area of ongoing research.
So it's like saying we're acknowledging that perfect knowledge
It's clear that there's a lot more to explore.
isn't always attainable, and that sometimes it's more meaningful to work with probabilities and ranges of possible outcomes.
Absolutely. And beyond the computational challenges.
Exactly. And this shift in perspective opens up a whole new realm
There are fundamental questions about the behavior of these measure-valued solutions.
of possibilities for analyzing these complex systems. It allows us to move beyond the limitations.
For example, how do they behave in the long term? Do they tend towards a stable equilibrium, or do they exhibit more complex, chaotic dynamics?
Of traditional approaches and develop.
And how do we connect these measure-valued solutions back to real-world observations and make predictions about the behavior of complex systems? These are all exciting avenues for further investigation.
A deeper understanding of the intricate interplay between individual actions and collective behavior.
Indeed. And the work presented in this paper is just the tip of the iceberg. The framework of dissipative, measure-valued solutions for the Euler alignment system is a powerful new tool for understanding collective behavior, and I'm confident that we will see many more fascinating discoveries and applications emerge from this line of research. You're right. Let's go back to our bird flock example. Imagine you're trying to model
Precisely.
the movement of the flock using the Euler alignment system. In a traditional approach, you would need to specify the exact position and velocity.
You're talking about those moments of
Each bird at every point in time.
when the collected behavior of a system transcends
But in reality, obtaining such precise information is often impossible.
the actions of its individual components. Think about the intricate patterns of a flock of birds.
You're right. It would be like trying to track every single dancer in a massive, constantly moving performance.
The coordinated movements of a school's fish or the complex structures built by ant colonies. These are all examples of emergent behavior.
Exactly. With a measure-valued solution, instead of trying to pinpoint the exact location
And understanding the principles behind them is a major challenge.
of each bird,
It's like each dancer
you can describe the probability of finding a bird within a certain region of space.
is following their own steps, but somehow
This probability distribution evolves over time according to the equations of the system, capturing the overall dynamics of the flock without requiring precise knowledge of each individual's position.
a beautifully coordinated performance emerges.
So it's like saying we're focusing on the overall flow and patterns of the flock rather than getting bogged down in the details of each bird's movement. This makes so much more sense now.
The challenge lies in connecting those individual actions to the collective patterns. How does order arise
Okay.
from seemingly chaotic individual movements?
The key is that this probabilistic description,
Measure-valued solutions
captured by the young measures we discussed earlier, offer a promising avenue for exploring these questions.
still allows us to extract meaningful information.
How so? It seems like we're moving further away from deterministic descriptions by embracing probabilities.
About the system,
Wouldn't that make it even harder to understand these emergent patterns?
we can calculate quantities like the average density or velocity
right.
of the flock,
Right.
the probability of the flock reaching a certain area, and other statistically relevant properties.
Quite the contrary.
So it's like shifting our focus from the individual dancers
Measure-valued solutions provide a way to analyze
to the overall choreography of the
the
performance
statistical properties
by looking at the statistical patterns.
of emergent behavior, for example. We can gain a deeper understanding of how the dance unfolds.
Instead of trying to predict the exact trajectory
Okay.
of each bird in a flock, we can study the distribution of flock shapes,
So it's like shifting our focus from the individual dancers
the average density of birds in different regions,
to the overall choreography of the performance.
or the probability of the flock splitting or merging.
By looking at the statistical patterns, we can gain a deeper understanding of how the dance unfolds.
These statistical properties provide insights into the underlying principles governing the flock's behavior as a whole.
Exactly. And this statistical lens can be applied.
Exactly. And this statistical lens can be applied to a wide range of systems exhibiting emergent behavior.
To a wide range of systems exhibiting emergent behavior.
We can study the flow patterns of traffic, the spread of information in social networks,
So we can study the flow patterns of traffic,
the dynamics of financial markets,
the spread of information in social networks,
and even the evolution of galaxies. Measure-valued solutions offer
the dynamics of financial markets, and even the evolution of galaxies. Measure-valued solutions offer a powerful new way to analyze and understand these complex systems, moving beyond the limitations of traditional approaches that struggle to handle uncertainty and nonlinearity.
a powerful new way to analyze and understand these complex systems, moving beyond the limitations of traditional approaches.
It out.
That struggle to handle uncertainty and non-linearity.
This is just the beginning.
This is truly groundbreaking. But as you've pointed out,
There are still many open questions and challenges ahead.
this is just the beginning.
Absolutely. This research has opened up a Pandora's box
There are still many open questions
of possibilities
and challenges ahead.
and raised a host of fascinating questions.
Absolutely.
For example, we need to develop more efficient and practical methods for computing these measure-valued solutions.
This research has opened up.
The computational costs can be quite high, especially for large-scale systems. Finding ways to make these computations more tractable is crucial for unlocking the full potential of this framework.
A Pandora's box of possibilities and raised.
So it's like we need better tools to analyze the choreography of these increasingly complex dances.
A host of fascinating questions.
Okay.
For example, we need to develop more efficient
Right.
and practical methods for computing these measure-valued solutions.
And beyond the computational challenges, there are fundamental questions about the long-term behavior of these measure-valued solutions. Do they tend towards a stable equilibrium? Do they exhibit oscillations or chaotic dynamics? How do these behaviors relate to the underlying parameters of the system?
The computational costs can be quite high, especially for large-scale systems. Finding ways
Sure.
to make these computations more tractable is crucial for unlocking.
And how do we bridge the gap between these theoretical models and real-world observations? Can we use these measure-valued solutions to make accurate predictions about the behavior of complex systems? Can we use them to design systems that leverage the principles of emergent behavior?
The full potential of this framework.
These are all exciting questions that researchers are actively exploring. This is a vibrant and rapidly evolving field, and I'm confident that we will see many groundbreaking discoveries and applications in the years to come.
And beyond the computational challenges.
It's incredible to think about the potential impact of this research.
There are fundamental questions about the long-term behavior.
It feels like we've just begun to explore.
Of these measure-valued solutions, do they
It's
tend
a vast and uncharted mathematical landscape.
towards a stable equilibrium? Do they exhibit oscillations or chaotic dynamics? How do these behaviors relate?
I couldn't agree more. The framework of dissipative measure-valued solutions for the Euler alignment system is a testament to the power of mathematics,
To the underlying parameters of the system.
to illuminate the mysteries of the world around us.
And how do we bridge the gap between these theoretical models
And as we continue to develop and refine these tools,
and real-world observations?
I believe we will unlock even deeper insights.
Can we use these measure-valued solutions to make
It is the fundamental principles governing complex systems.
accurate predictions about the behavior?
Well, on that inspiring note, I think it's time to wrap up part 2 of our deep dive
Of complex systems.
into the Euler alignment system.
Can we use them to design systems?
Agreed. We've delved into the intricacies of the weak-strong uniqueness principle, explored the significance of measure-valued solutions, and even glimpsed the vast landscape of potential applications.
That leverage the principles of emergent behavior.
Join us in part 3, where we'll step back to ponder some of the broader implications of this research, explore potential avenues for future exploration, and perhaps even encounter some provocative questions that challenge our assumptions about how we understand the world around us. Welcome back to our final exploration of the Euler alignment system. I feel like we've been on an incredible journey
It has been quite an adventure.
through a mathematical landscape
Yep.
filled with, intricate concepts and fascinating insights.
Hasn't it? We've laid out the groundwork.
Now, let's take a step back
Delved into the intricacies of measure-valued solutions.
and ponder some of the broader questions that arise from this research.
And explored the implications of this powerful new framework. Now let's take a step back and ponder
I'm ready to dive into the deep end of thought.
some of the broader questions that arise from this research.
That's a question that really makes you think about this work differently.
For me,
Okay.
it's the profound implications of these measure-valued solutions
Okay.
for how we understand predictability and determinism.
You're right. It's like acknowledging that even with perfect equations, we might not be able to predict the exact outcome.
In complex systems, we often think of solutions to mathematical equations as providing precise, definitive answers.
There's an element of uncertainty woven into the very fabric of these systems.
But these measure-valued solutions challenge that notion.
Okay.
Exactly. And it's not simply a matter of lacking complete information.
Okay.
It's a deeper recognition that these systems are inherently probabilistic.
That's a fascinating perspective. It's like saying that instead of seeking a single perfect choreography,
The focus shifts from finding the solution.
we're acknowledging that the dance can unfold in many different ways, all within certain probabilistic constraints.
to characterizing a range of possible behaviors.
So instead of clinging to the illusion of perfect predictability, we embrace the richness of possibilities.
Each with its own probability.
Precisely.
Precisely. This has profound implications.
This has profound implications for how we model and analyze complex systems.
For how we model and analyze complex systems.
It suggests that we need to develop tools and techniques.
It suggests that we need to develop tools and techniques that can handle
this inherent uncertainty and extract meaningful information from these probabilistic descriptions.
this inherent uncertainty.
That brings us to another intriguing question. How can we use these measure-valued solutions to better understand emergent behavior? It's those, mesmerizing patterns that arise from the seemingly simple interactions of individuals in a group.
And extract meaningful information from these probabilistic descriptions.
Okay.
You're talking about those moments when the collective behavior of a system transcends the actions of its individual components. Think about the intricate patterns of a flock of birds.
It's like each dancer is following their own steps.
The coordinated movements of a school of fish, or the complex structures
But somehow a beautifully coordinated performance emerges.
built by ant colonies. These are all examples of emergent behavior.
Okay.
And understanding the principles behind them
Right.
is a major challenge.
The challenge lies in connecting those individual actions to the collective patterns.
It's like each dancer.
How does order arise from seemingly chaotic individual movements? Measure-valued solutions offer a promising avenue
Is following their own steps.
for exploring these questions.
But somehow, a beautifully coordinated performance emerges.
Okay,
The challenge lies in connecting those individual actions.
how so? It seems like we're moving further away from deterministic descriptions by embracing probabilities.
To the collective patterns, how does order arise?
Wouldn't that make it even harder to understand these emergent patterns?
From seemingly chaotic individual movements.
Okay.
Measure-valued solutions offer a promising avenue for exploring these questions. Quite the contrary.
Quite the contrary.
Measure-valued solutions.
Measure-valued solutions provide a way to analyze the statistical properties of emergent behavior.
Provide a way to analyze.
For example, instead of trying to predict the exact trajectory of each bird in a flock, we can study the distribution of flock shapes, the average density of birds in different regions, or the probability of the flock splitting or merging. These statistical properties provide insights into the underlying principles governing the flock's behavior as a whole.
The statistical properties of emergent behavior. For example, instead of trying to predict the exact trajectory,
So it's like shifting our focus from the individual dancers to the overall choreography of the performance.
of each bird in a flock, we can study the distribution.
By looking at the statistical patterns, we can gain a deeper understanding of how the dance unfolds.
Of flock shapes.
Okay.
The average density of birds in different regions. Or the probability of the flock splitting or merging. These statistical properties provide insights into the underlying principles governing the flock's behavior.
And this statistical lens can be applied to a wide range of systems exhibiting emergent behavior.
As a whole.
We can study the flow patterns of traffic, the spread of information in social networks, the dynamics of financial markets, and even the evolution of galaxies. Measure-valued solutions offer a powerful new way to analyze and understand these complex systems, moving beyond the limitations of traditional approaches that struggle to handle uncertainty and non-linearity.
Exactly. And the statistical lens.
This is truly groundbreaking. But, as you've pointed out, this is just the beginning.
Can be applied to a wide range of systems.
There are still many open questions and challenges ahead.
Exhibiting emergent behavior.
Okay.
We can study the flow patterns of traffic, the spread of information in social networks.
Absolutely. This research has opened up a Pandora's box of possibilities
The dynamics of financial markets.
and raised a host of fascinating questions.
And even the evolution of galaxies. Measure-valued solutions offer a powerful new way.
For example, we need to develop more efficient and practical methods for computing these measure-valued solutions.
To analyze and understand these complex systems, moving beyond the limitations of traditional approaches that struggle.
The computational cost can be quite high, especially for large-scale systems. Finding ways to make these computations more tractable is crucial for unlocking the full potential of this framework.
To handle uncertainty and nonlinearity.
So it's like we need better tools to analyze the choreography of these increasingly complex dances.
This is truly groundbreaking, but as you've pointed out, this is just the beginning. There are still many open questions and challenges ahead. Absolutely. This research.
And beyond the computational challenges, there are fundamental questions about the long-term behavior of these measure-valued solutions. Do they tend towards a stable equilibrium? Do they exhibit oscillations or chaotic dynamics? How do these behaviors relate to the underlying parameters of the system?
Has opened up a Pandora's box of possibilities and raised a host of fascinating questions.
Right.
For example, we need to develop more efficient and practical methods.
And how do we bridge the gap between these theoretical models and real-world observations? Can we use these measure-valued solutions to make accurate predictions about the behavior of complex systems? Can we use them to design systems that leverage the principles of emergent behavior?
For computing these measure-valued solutions.
These are all exciting questions that researchers are actively exploring. This is a vibrant and rapidly evolving field, and I'm confident that we will see many groundbreaking discoveries and applications in the years to come.
The computational costs can be quite high.
It's incredible to think about the potential impact of this research. It feels like we've just begun to explore a vast and uncharted mathematical landscape.
Especially for large-scale systems. Finding ways.
I couldn't agree more. The framework of dissipative, measure-valued solutions for the Euler alignment system is a testament to the power of mathematics to illuminate the mysteries of the world around us. And as we continue to develop and refine these tools, I believe we will unlock even deeper insights into the fundamental principles governing complex systems. Well, on that inspiring note, I think it's time to wrap up our deep dive into the Euler alignment system. Thank you for joining us on this intellectual adventure.
It's been a pleasure to share the wonders of mathematics with you. I hope this exploration has sparked your curiosity and left you with a sense of awe at the beauty and complexity of the world we live in.
Welcome back to the Deep Dive. You've been exploring this fascinating mathematical model, the Euler alignment system, and how it helps us understand these really, what looks like choreographed movements of animal swarms, from flocking birds to schooling fish.
Yeah.
Today, we're taking this model to the next level.
Okay.
Exploring something called dissipative measure-valued solutions.
Okay.
And a principle known as weak, strong uniqueness. I have to admit, those sound a little intimidating.
Yeah.
But thankfully, you sent over some excerpts from an academic paper that dives into these very concepts. So maybe we can unpack them together.
Yeah, absolutely.
Let's start with the paper itself. It's called Dissipative Measure-Valued Solutions and Weak, Strong Uniqueness for the Euler Alignment System.
All right.
Quite a mouthful.
Yeah.
What's the core problem that the researchers are tackling here?
So, they're really trying to understand, like, okay, how does this, Euler alignment system work when you have what they call, like generic initial data?
Yeah.
So instead of saying, okay, let's look at this, simplified, idealized scenario, they're saying, okay, in real world swarms, the initial conditions, where are they? How fast are they moving? It can be messy and unpredictable.
Okay, so things are getting real. How do they even begin to approach that kind of complexity?
So this is where this idea of a dissipative measure-valued solution comes in. Imagine, right, you're trying to analyze the movement of a massive flock of birds.
Okay.
Right. Now, to track each individual bird would be a computational nightmare.
Right.
Right. So what they do is you kind of step back.
Yeah.
You look at the flock as a whole, almost like a cloud of birds.
Got it. So we're zooming out to see the bigger picture, not getting lost in the feathers.
Exactly. Yeah. So a measure-valued solution is kind of like a snapshot of this cloud. At a particular moment, it doesn't tell you precisely where each bird is, but it gives you information about the overall distribution of the flock, its density, average velocity, and so on.
So it's a way to grasp the essence of the swarm's behavior without getting bogged down in the minutia of each individual bird's movement.
Exactly.
That's awesome. And, the paper actually mentions that these measure-valued solutions are particularly useful because they can handle limits of various approximation methods.
Right.
It's like saying, even if we can't perfectly track every single bird, these solutions still provide valuable insights.
Yeah, exactly. And then, so the other part of the name is this dissipative. Right. So dissipative refers to the fact that, these systems naturally lose energy over time. like
Mm.
just right, like any real world system.
Right.
So you think about like air resistance or friction.
Right.
These cause a loss of energy.
So it's like the swarm is slowly leaking energy as it moves.
Precisely. And then the paper talks about the dissipation defect,
Mm-hmm.
which is a way to like quantify how much energy is being lost.
Interesting. And understanding how that energy dissipates could be crucial for predicting, how the swarm's movements might evolve over time.
Absolutely.
Now, the paper also mentions this weak, measure-valued, strong uniqueness principle.
Okay.
What in the world does that mean?
So this, it might sound really complicated, but the idea is actually pretty intuitive.
Okay.
Imagine you have two different ways of describing the same flock of birds.
Mm-hmm.
One is what they call a smooth solution, which is kind of like, it's perfectly predictable, well-behaved, kind of like this, idealized model.
Okay.
And then the other one is our measure-valued solution, which is kind of like, more like that statistical snapshot of the flock.
So like one's like a precise blueprint and the other's like a more impressionistic painting.
That's a great analogy. And so the weak, strong uniqueness principle is essentially saying, if these two descriptions start from the same point, they will remain identical as long as that smooth solution exists.
Oh.
Okay. So it's like saying that our less precise snapshot of the flock is trustworthy as long as some theoretical perfect flock
Right.
is behaving the same way.
Exactly. So it's a powerful principle because it links the simpler world of smooth solutions to the more complex world of measure-valued solutions.
Right.
So it gives us confidence that even our less precise models can still capture the essence of the behavior.
Okay. So we've got these measure-valued solutions that give us a handle on complex initial conditions. And we have this principle that assures us that they're so reliable as long as some idealized smooth solution exists. What kind of math heavy lifting did the researchers do to arrive at these concepts?
Okay, so they introduced a few key tools
Yeah.
to prove their points.
Mm-hmm.
One of them is, it's called a binary tensor Young measure.
Oh.
Now that sounds like,
Sounds like Star Trek or something.
Yeah, exactly. But it's really just a way of making sense of the interactions between different parts of the swarm.
Okay. Break it down for us. What are these interactions and why is this measure so important?
So imagine you have two groups of birds within the flock.
Okay.
Right. Now the movement of one group might influence the movement of the other group. Right. So this binary tensor Young measure allows us to quantify and analyze those influences. It's kind of like, mapping out the choreography of their aerial dance.
Yeah. So it's a way of understanding the interconnectedness of the swarm, how each part influences the whole.
Precisely.
That's awesome.
So then they go on to kind of mathematically define exactly what, a dissipative measure-valued solution is.
Yeah.
And what conditions it must satisfy.
Yeah.
So, they start off, they define a spacie, which is just R sub times, a time interval 0 to infinity.
Okay.
Right? This is just for the, velocities and densities.
So they're setting up the stage, defining the variables and the space where all the action's going to take place.
Right. Yeah, exactly. So then they go on to define this binary tensor Young measure, which is denoted as pook small.
Okay.
And so basically this is defined as a product measure sub to sub where subtext sub is just the Young measure itself. So it's a mapping from, time and space into a probability measure on U.
That's quite a mouthful. Can you unpack that a bit for us?
Yeah, so think of it this way. The Young measure, subset sub, basically tells us the probability of finding a certain density and velocity at a specific point in space and time.
Okay.
So the binary tensor Young measure, subtext sub, basically extends that idea to pairs of points.
Okay.
So now we can analyze the joint probability distribution of density and velocity at two different locations.
So it's like a two-dimensional probability map showing us how the state of the swarm at one point is correlated to the state at another point.
Exactly.
That's really cool.
Yeah, and so this binary tensor Young measure has some interesting properties.
Okay.
That makes it particularly useful for studying swarm behavior.
Okay.
So firstly, it exhibits symmetry.
Okay.
So what that means is if we swap the positions X and Y in the measure, it doesn't actually change the outcome.
Okay.
Mathematically, they write this as like, ho sub 2 sub subtabs xi sub ss vs vs equals hat sub top subs y sub s via for almost every point in time and space, where f is just any continuous function on u sub 2's.
So it's saying that the interaction between two parts of the swarm doesn't depend on which part we consider first.
Right.
The influence goes both ways.
Exactly. Yeah. And secondly, it has this property of consistency.
Okay.
So basically what that means is, like, if we look at a function, right, that only depends on one part of the swarm, the binary tensor Young measure behaves just like the regular Young measure.
Gotcha.
So we can write this mathematically as if, f in C sub 0 sub C sub is of the form FSV SV equals GUSV, where G is just some continuous function on U. Then A sub 2 x COC sub FC hey sub XIE for almost every 2xy.
So it's saying that if we zoom in and focus on a single point, the binary tensor Young measure simplifies to the regular Young measure, giving us a consistent description at different scales.
Precisely. Yeah.
Okay. So these properties are really important because they demonstrate that the binary tensor Young measure isn't just like some arbitrary mathematical construct, but a tool that's deeply connected to the underlying dynamics of the system we're studying.
Right.
Which, makes sense.
Yeah.
Right.
Yeah.
A tool designed to study interactions should itself reflect the nature of those interactions.
Absolutely, yeah.
So to formally define a dissipative measure-valued solution, they lay out a series of conditions that must be satisfied.
Right.
The first one is that, our Young measure must be weak measurable.
Yeah.
This is kind of a technical condition that ensures that we can, meaningfully talk about averages and integrals involving this measure. So it's like saying, to work with this measure, it needs to behave nicely when we do calculations with it.
Exactly. Yeah.
Then they impose a boundedness condition.
Okay.
Which can be expressed as like subset plus substitute sub. So this condition ensures that the total mass and energy of the swarm, as described by our measure of valued solution, remain bounded over time.
Exactly.
Which makes sense. We can't have swarms like spontaneously gaining infinite mass or energy, right? That would just violate the laws of physics.
Exactly. And then they talk about the dissipation defect, which we talked about earlier.
Right.
This quantity must belong to L suppo T and be, non-negative.
Right. It's always positive because energy can only be lost, not gained in these dissipative systems.
Exactly. Yeah.
Now, we get to the heart of the dynamics.
Okay.
The equations that govern, how the swarm evolves over time. And the first is the equation of continuity, which in fluid dynamics represents the conservation of mass. So it's like saying no bird can magically disappear or appear out of thin air.
Right.
The total number of birds must remain constant.
Yeah, exactly. So this condition basically states that there exists a measure or sub C sub that's in L superior T MT sub that basically controls how mass is transported within the swarm, and its magnitude is bounded by the dissipation defect. Mathematically, they write this as surp sup TD sub, for almost every N0T, where, it's just some function of time.
Right.
Is this just a test function from C sub sup N C sub. And the notation sup basically represents the action of the measure sup on the gradient of sup.
Okay.
And along with this, they also specify this like integral equation involving the Young measure, its initial value, and this sub C sup that must hold for a set of suitable test functions.
Okay.
So this basically describes how the overall density of the swarm evolves over time.
Got it. So the equation of continuity keeps track of the mass, ensuring that it's conserved as the swarm moves and changes shape.
Yeah.
What's next?
So then next we have the momentum equation, which basically describes the conservation of momentum.
Okay.
So in simpler terms, this tells us how the swarm's movement is influenced by forces.
So it's like Newton's second law for the entire swarm. Force equals mass times acceleration, but, for a collective entity.
Right. Exactly. So similar to the continuity equation, there exists this measure, a sub that controls how momentum is transported.
Okay.
And it's also linked to the dissipation defect D.
Okay.
So they write this mathematically with an inequality sub 60 subs TD sub for almost every pre, where x is just a function of time, and it's a test function from c sub 0 tx sub sub.
Okay.
And just like with the continuity equation, they provide another, integral equation that basically captures how the swarm's overall velocity changes over time due to, forces like the pressure and, the alignment interactions.
Right.
And, this equation involves, again, the Young measure, sup, and the initial momentum.
Okay. So the momentum equation takes into account all the forces acting on the swarm. And tells us how it will accelerate and change direction.
Right.
What other conditions do they impose?
Okay, so then we have the energy inequality.
Okay.
So this condition basically reflects the fact that, the total energy of the system can only decrease over time due to dissipation.
So it's like saying that the swarm can't just like magically gain energy out of nowhere. It can only lose energy due to friction, air resistance, and other dissipative forces.
Exactly. So they write this mathematically, as for almost every moment in time, like the total energy of the swarm, as captured by the Young measure, plus the accumulated dissipation defect must be less than or equal to the initial energy.
Got it.
So they write this as sub 12 sub plus t got sub. So here P represents like the pressure potential, which basically captures the energy associated with the density of the swarm. So the second term in this inequality quantifies the energy dissipated through the alignment interactions between different parts of the swarm.
So it's like saying that the initial energy pie can only shrink, not grow.
Right.
And we're keeping track of how much of that pie is lost due to both like internal friction and the interactions between different parts of the swarm.
Exactly, yeah.
What else do we need to pin down this definition?
So the next condition is what they call a compatibility condition.
Okay.
So if you have a smooth function, this condition establishes a relationship between the variance of the velocity field as captured by the Young measure and the dissipation defect.
It seems like this condition is connecting the smoothness of a hypothetical reference velocity field to the energy dissipation in the system.
That's a good way to put it. Yeah. So they write this mathematically as for almost all v and u are just the averages of the velocity fields v and u.
Right.
And sub is just some positive constant that depends on the alignment interaction strength.
Okay. So this condition is ensuring that our measure-valued solution is behaving consistently with any hypothetical smooth solution we might have for the Euler alignment system.
Precisely.
Yeah, cool.
And then finally, they impose conditions on the support of EAD.
Okay.
So essentially what this says is that the density component of the solution must be bounded away from zero.
Well, that makes sense, right? We can't have like, a negative number of birds in a flock.
Right, exactly.
Okay.
So they express this by stating that, there exists a positive constant sub such that sub 2 sub 0 8 verse sub 0 over 0 sub and suppose sub 0 v are sub 0 and v sub for almost every txy in the time-space domain.
Okay.
So this basically ensures that the measure-valued solution only assigns, positive values to density,
right,
which, reflects the physical constraints of the system we're modeling.
It's like they're embedding common sense to the mathematical framework.
Right.
So now that we've meticulously laid out all these conditions,
right,
what do the authors actually do with this definition of a dissipative measure-valued solution?
Okay, so that's where things get even more interesting.
Okay.
So their first major result, which they call Theorem 2.1, basically involves showing that a sequence of solutions to a regularized version of the Euler alignment system converges to a dissipative measure-valued solution.
Hold on. What do they mean by regularized?
adding a bit of artificial viscosity
Right.
to smooth things out. So that's what regularization is all about.
It kind of makes the equations a bit more well-behaved.
Yeah.
So we can find solutions more easily.
Right, like adding a little bit of oil to a machine to make it run smoother. So how do they go about proving this convergence?
Okay, so the first step is to basically identify the weak limits of the sequences of densities and velocities from this, regularized system.
Okay.
Right, so we have these, increasingly smooth solutions thanks to the artificial viscosity.
Right.
And we want to see, okay, where did they settle as we gradually remove that smoothing effect?
It's like watching a spinning top gradually slow down and seeing where it finally comes to rest.
Precisely.
Got
So
it.
to do this, they rely on the energy estimate from the regularized system and the assumption that the densities are bounded below by a positive constant.
So this gives them uniform bounds on the densities and velocities in various function spaces.
Got it.
Right. So it makes sure that these sequences don't blow up as we take the limit.
So they're making sure that the solutions stay within, certain bounds.
Yeah.
That they don't suddenly
Right.
shoot off to infinity or become nonsensical.
Exactly. Yeah. And so with these bounds in hand, they can apply standard weak compactness arguments.
Okay.
So these arguments essentially say that if you have a sequence of functions that are, well behaved in a
Right.
certain sense,
Yeah.
then you can always extract a subsequence that converges, albeit in a weaker sense.
So even if our functions are getting a bit wild as we remove the smoothing, we can still find a subsequence that settles down in a predictable way.
Exactly. And that settling down is described by the Young measure, which basically captures that limiting behavior of these sequences.
That's it.
So they use this notation sup1, sup-subtext, subtext, sup-subtick x, use a tick x,
Okay.
to represent the Young measure associated with the density and velocity at a particular time
Okay.
and spatial point
Yeah.
for a specific value of the artificial viscosity.
Okay, so this notation is basically saying, here's the Young measure that corresponds to this particular density and velocity at this particular point
Right, exactly.
in space and time. Okay.
And as Stuka-Pasuk goes to zero,
Yeah.
meaning we're removing that artificial viscosity,
All right.
they show that this Young measure converges weak
Okay.
in a supa sub weak sub 0 tx sup sub pu to this limiting Young measure sub tick sub.
Now you've used the term weak convergence a couple of times.
Right.
Can you remind us what that means?
Of course. Yeah, so the weak
Mm-hmm.
basically just signifies a specific type of convergence that's appropriate for measures. So it ensures that averages and integrals involving these measures converge as expected.
Okay.
And the space sub weak sub 0 tx sub pu is basically the natural setting for these Young measures because, it captures their time-dependent and spatially distributed nature.
So it's like saying we need to use the right kind of convergence to make sure our calculations with these measures make sense
Right.
in the context of time and space.
Precisely, yeah. And so they do a similar thing for the binary tensor Young measure, right? They define it for the regularized system as sup 2 sub t x sub t x sub t 6 sub t sub e sub t x u sub t.
Okay.
And they show that as x sub 2 sup approaches 0, this converges weak in L sub 2 sup to this limiting binary tensor Young measure sub text sub.
Okay, so they're showing that both the regular Young measure and the binary tensor Young measure converge to something meaningful as we remove the artificial viscosity.
Exactly.
Okay.
And so these convergences are really crucial
Yeah.
for establishing that the limit of these regularized solutions actually satisfies the conditions for a dissipative measure-valued solution.
Right.
Right. So, for instance, they use these convergences to show that the continuity equation, which we talked about earlier, is satisfied in the limit.
So even as we remove the smoothing effect of the viscosity, the fundamental principle of conservation of mass still holds.
Exactly. Yeah.
Now the momentum equation is a bit trickier.
Yeah. So the momentum equation is a bit trickier.
Yeah.
You have to show that the viscosity term actually vanishes in the limit.
Right.
Since we're letting that artificial viscosity coefficient go to 0.
Right.
So this requires careful analysis, using the properties of the viscosity coefficient and the estimates they've derived for the density and velocity.
So it's like saying we introduced this artificial viscosity to make things easier, but now we need to make sure that it disappears gracefully as we approach the real solution.
Exactly. And they also need to show that the non-local alignment interaction term converges to the correct form in the limit.
Right.
So this involves using the properties of the binary tensor Young measure, and carefully analyzing the behavior of this singular kernel that's associated with the fractional Laplacian operator.
Right. It's the choreography of their movement.
Exactly.
So they're making sure that even in the limit, as the smoothing effect disappears, those interactions are still accurately accounted for.
Yeah, exactly. So, and then they have to show that the energy inequality holds in the limit.
Yeah.
Right, so remember, this inequality reflects the fact that energy can only be lost due to dissipation. So to show this, they use the fact that the energy functional is lower semi-continuous, which is just a fancy way of saying it behaves nicely under limits.
Okay.
And they also demonstrate that the compatibility condition and the constraints on the support of the Young measure are satisfied in the limit.
So they're ticking off all the boxes, making sure that this limiting solution really does satisfy all the conditions we laid out earlier.
Exactly.
For a dissipative measure-valued solution.
Yeah, and with that, they complete the proof of Theorem 2.1, demonstrating that under suitable conditions, these regularized solutions converge to a fully fledged dissipative measure-valued solution.
That's a pretty impressive feat of mathematical maneuvering.
It is, and it lays the groundwork for studying the Euler alignment system in a much more general and robust way.
Yeah.
But now we get to the really exciting part, Theorem 2.2, which establishes the weak measure-valued strong uniqueness principle.
Yes. The principle that tells us our rough sketch of the flock stays accurate as long as the satellite image remains clear.
Right.
How do they go about proving that?
So the strategy is to derive what's called a relative energy inequality.
Yeah.
So this involves comparing the dissipative measure-valued solution and the smooth solution using a specific mathematical tool called a relative energy functional.
So this functional is like a ruler that measures the distance between these two different ways of describing the swarm.
Yeah.
Okay.
So this functional is denoted by E sub mv open parenthesis s comma u double bar r comma u close parenthesis open parenthesis tau close parenthesis.
Okay.
And it takes into account the density and velocity from both solutions at a particular time tau. So here, open parenthesis s comma u close parenthesis represents the density and velocity associated with the measure-valued solution.
Okay.
While open parenthesis r comma u close parenthesis represents those of the smooth solution.
Okay, so it's looking at both the cloudiness of the flock, which is the density, and how fast it's moving, which is the velocity.
Right.
And comparing those aspects between the two solutions.
Exactly. And the functional itself is defined as E sub mv open parenthesis osec comma u double bar r comma u close parentheses open parenthesis tau close parenthesis equals the integral over t to the d of the expectation with respect to the Young measure nu sub tau comma x of 1/2 times the absolute value of v minus u of tau comma x squared plus p of s minus p prime of r of tau comma x times the quantity s minus r of tau comma x minus p of r of tau comma x dx.
That looks pretty intense.
Oh.
Can you unpack that a bit?
Of course. So we have an integral over the spatial domain t to the d, and inside we're taking the expectation of a function with respect to the Young measure nu sub tau comma x.
Okay.
So this expectation gives us the average value of the function over all possible densities and velocities at a point x in time tau based on the measure-valued solution.
Okay. So it's like taking a weighted average where the weights are determined by how likely each density and velocity value is according to the measure-valued solution.
You got it. Now let's look at the function we're averaging. It has three main parts. The first part, 1/2 s times the absolute value of v minus u of tau comma x squared, seems to be measuring the difference in kinetic energy between the two solutions at each point.
Right. It's looking at how much the velocities differ.
Exactly. The other parts, p of s minus p prime of r of tau comma x times the quantity s minus r of tau comma x minus p of r of tau comma x, are all related to the pressure potential P.
Okay.
They quantify the difference in potential energy due to pressure,
Okay.
which is essentially how much the densities differ.
So the functional is adding up the differences in both kinetic and potential energy between the two solutions,
Right.
weighted by the probabilities given by the measure-valued solution.
You've got it. And the author's goal is to show that this relative energy functional can be controlled over time. If they can do that, it means the measure-valued solution can't wander too far from the smooth solution.
Like keeping the rough sketch tethered to the satellite image.
Right.
Okay,
Yeah.
so how do they go about controlling this functional?
They start by cleverly using the equations that define a dissipative measure-valued solution. Remember all those conditions we went through?
Right.
They use those conditions to rewrite the relative energy functional in a more manageable form.
So they're strategically applying the rules of the game
Right.
to simplify things.
Exactly.
Yeah.
For instance, they use the continuity equation with a specific test function to get an expression for how the kinetic energy associated with the smooth velocity field U changes over time.
Okay.
They also use the continuity equation with a different test function to track how the potential energy, which is tied to the smooth density fielder, changes over time.
So it's like they're carefully selecting the right tools from their toolbox to analyze each aspect of the relative energy.
Right. And they also apply the momentum equation using the smooth velocity field as a test function.
Okay.
This gives them an expression for how the velocity fields of the two solutions interact over time.
So they're systematically accounting for all the ways in which the two solutions can influence each other.
Precisely. And after all this manipulation, they're able to rewrite the relative energy functional in a very specific form.
Okay.
It includes the initial data, the dissipation defect D, and several integral terms that represent the interplay between the two solutions.
So it's kind of like disentangling, not separating the relative energy into different pieces that can be analyzed individually.
Great analogy. And now the hard work begins. They have to estimate each of those integral terms very carefully, using the properties of both the smooth and measure-valued solutions, as well as some powerful inequalities from functional analysis.
Sounds like a delicate and intricate process. Could you give us a taste of some of the techniques they use?
Absolutely. For some terms, they use the fact that the smooth solution is well smooth. This means its spatial gradients are bounded, which allows them to make certain estimations. For other terms, they use the fact that certain functions like the pressure potential P are convex, which provides them with useful inequalities.
So they're drawing on a broad mathematical arsenal, adapting their approach to each specific term.
Exactly. And they also leverage the compatibility condition, which we discussed earlier.
Right.
Remember, this condition links the smoothness of the reference velocity field to the energy dissipation in the system.
Right.
This helps them control certain terms that would otherwise be very difficult to handle.
It's like they're using every tool at their disposal to bring these complex terms under control.
Right. They even use a smooth cutoff function, which is a mathematical trick to isolate and analyze different parts of the solution's support. This helps them deal with terms that might otherwise blow up to infinity.
So it's like putting a safety net under a tightrope walker. It allows them to take risks without falling into the abyss of mathematical chaos.
Exactly. After all this meticulous work, they finally arrive at an inequality that bounds the relative energy at time tau by its initial value, plus a term involving the integral of the relative energy itself over time.
So it's like saying the distance between the two solutions at some point in time can't be too much larger than the initial distance plus the accumulated distance over time.
Precisely. And this particular form of inequality is perfect for applying a powerful mathematical tool known as Gronwall's lemma.
Gronwall's lemma. I've heard whispers of its legendary power in the halls of mathematical lore. What makes it so special?
Gronwall's lemma is like a mathematical time machine. It lets us trace the evolution of a quantity back to its initial state. In this case, it allows us to convert the integral inequality, which involves a relative energy over a time interval, into a simpler inequality that only involves the relative energy at a specific time.
So it's like condensing all that accumulated history into a single snapshot.
Exactly. And when they apply Gronwall's lemma, they get the final form of the relative energy inequality.
Okay.
This inequality bounds the relative energy at time tau by its initial value, multiplied by a constant that depends on the time interval and various parameters of the system.
Okay, so even as the system evolves, the distance between the two solutions is ultimately controlled by their initial distance.
Exactly. And this, my friend, is the heart of the weak, strong uniqueness principle. If the two solutions start at the same point, meaning their initial relative energy is 0, then this inequality guarantees that they stay together. Their distance remains 0 for all times as long as the smooth solution exists.
It's like they're two dancers, perfectly synchronized, moving in unison across the mathematical stage.
That's a beautiful way to put it. It's a testament to the elegant connections between different types of solutions in mathematics, and it gives us confidence that these measure-valued solutions, even though they're more complex, are still fundamentally tied to the simpler, more intuitive world of smooth solutions.
It's really amazing how, we can use this principle to like keep our measure-valued solutions grounded.
Yeah.
It's like they have this mathematical tether that prevents them from drifting too far from reality.
Absolutely.
Now, the authors don't stop there. They actually go on to explore a specific type of approximation to the Euler alignment system called the density-dependent viscosity equations.
Right.
So can you tell us a little bit about that?
Yeah, so these equations basically introduce a smoothing effect that depends on the density of the swarm.
Okay.
So it's kind of like saying the more crowded the flock, the more resistance they experience, which helps prevent them from bunching up too tightly.
That's a fascinating concept. So it's almost like introducing a bit of like friction that increases as the swarm gets denser.
Exactly. Yeah. And the authors show that under certain conditions, the solutions to these density-dependent viscosity equations converge to a dissipative measure-valued solution of the original Euler alignment system.
So it's like we're adding a bit of like artificial friction to smooth things out.
Right.
And then carefully taking the limit as that friction disappears. And in doing so, we arrive at one of these measure-valued solutions, which are capable of capturing the more complex and realistic behavior of the swarm. That's awesome.
Yeah. And so this convergence result is significant, I think, for a couple of reasons. Firstly, it provides another concrete way to actually construct these measure-valued solutions. Remember, Theorem 2.1 gave us one way by taking the limit of the regularized solutions, and now we have another approach. Using these density-dependent viscosity equations.
It's like having multiple paths leading to the same destination, which gives us more confidence that we're on the right track.
Exactly. And secondly, it highlights the robustness of the measure-valued solution framework. It's capable of accommodating different types of approximations and still providing meaningful insights into the limiting behavior of those approximations.
It's like a flexible and powerful tool that can be adapted to different situations without losing its effectiveness.
Absolutely.
That's really cool. So to be a bit more precise, can you tell us a little more about these density-dependent viscosity equations? Like what form do they take?
Yeah, so these density-dependent viscosity equations, they take a specific form. So basically it involves two main equations. The first one is the continuity equation for the density sub plus div sub equals 0.
So this equation is still enforcing the conservation of mass.
Yeah.
You're making sure that the total number of birds in the flock doesn't magically change.
Exactly, yeah. And then the second equation is the momentum equation, which now includes this, additional viscosity term. So we have sub plus div sub do sub plus sub do sub in sub 0 too.
Okay, so we still have the terms representing like the inertia of the swarm, the pressure forces, and the alignment interactions. But now we have this extra term involving div sub do sub.
Exactly, yeah. So this is the viscosity term, and it involves a few kind of key ingredients. Firstly, we have, a sub, which is our artificial viscosity coefficient.
That's the artificial friction that we're gradually removing.
Yeah, exactly. And then we have a sub, which is the density-dependent viscosity coefficient. So this is the function that basically determines how strong the viscosity is based on the density of the swarm.
So the higher the density, the stronger the viscosity.
Exactly. And then finally we have du sub, which is the symmetric gradient of the velocity field. So this basically captures how the velocity is changing in different directions.
So the viscosity term is essentially saying that the rate at which the velocity changes is influenced by both the density of the swarm and that artificial viscosity coefficient.
Precisely, yeah. And, to make sure that this viscosity term actually does its job of smoothing things out,
Yeah.
the authors impose some conditions on the viscosity coefficient.
Okay.
So they require that it be continuously differentiable and satisfy the following inequality.
Okay.
Sub 1 plus super 1 plus super for all SS.
Mm-hmm.
Where sub and C sub are just positive constants.
Okay.
And LS is just a parameter that controls the strength of the density dependence.
So they're making sure that the viscosity is strong enough to prevent any nasty singularities from forming in the solutions, but
Right.
still allowing for the kind of the complex and potentially discontinuous behavior that we're interested in capturing.
Right.
It's like finding that sweet spot between too much smoothing and not enough. Awesome. So with these conditions in place, how do they go about analyzing the solutions?
Okay. So with these conditions in place, they can start analyzing the solutions to these density-dependent viscosity equations.
Mm-hmm.
So firstly, they derive what are called a priori estimates. So these are essentially bounds on the solutions that hold regardless of the specific initial conditions.
So it's like saying no matter where we start,
Right.
we know the solutions will always stay within these limits.
Exactly. So these estimates are really crucial for establishing the compactness of the sequence of solutions,
Okay.
which is a necessary step for extracting a convergent subsequence.
Right.
So to get these estimates, they first establish an energy estimate,
Okay.
which bounds the total energy of the system by its initial value.
Okay.
This follows from the dissipative nature of the system. Remember, the viscosity term
Right.
introduces additional energy dissipation.
So the energy can't grow out of control because it's constantly being leaked away by the viscosity.
Exactly. And then they derive estimates for the density and velocity in various Sobolev spaces, which are just mathematical spaces that measure the smoothness and integrability of functions.
Right.
So these estimates rely heavily on the specific structure of the density-dependent viscosity equations and the properties of the viscosity coefficient.
So they're digging deep into the mathematical machinery to get a really precise handle on how these solutions behave.
Precisely.
Yeah.
And so these estimates, especially the ones in Sobolev spaces, provide the necessary ingredients to apply this really powerful tool from functional analysis called the Aubin-Lyons-Simon compactness lemma.
Oh, another one of those powerful lemmas. What does this one do for us?
Yeah. So this lemma essentially states that if you have a sequence of functions that are bounded in certain Sobolev spaces, and their time derivatives are also bounded in a weaker sense.
Yeah.
Then you can extract a subsequence that converges strongly in an intermediate Sobolev space.
So it's like a mathematical filter, allowing us to pick out the good parts of the sequence that converge nicely.
Exactly. And that strong convergence is crucial for showing that the limit of these solutions actually satisfies the conditions for a dissipative measure-valued solution.
So the compactness lemma is like the bridge that allows us to connect, the world of these approximate solutions to the world of these more general measure-valued solutions.
Exactly. And once they have this, convergent subsequence, the authors can, analyze the limiting behavior of each term in the density-dependent viscosity equations.
Right.
So, they show that the continuity equation is satisfied in the limit, which is fairly straightforward given the strong convergence they've established.
So the conservation of mass survives the limiting process, which makes sense.
Yeah.
Now, what about the momentum equation?
Right. So the momentum equation requires a bit more careful attention.
Right. That one seemed a bit more complicated.
Yeah. So they have to show that the viscosity term actually vanishes in the limit as that artificial viscosity coefficient O goes to 0.
Right.
So this involves, using the properties of the viscosity coefficient and the estimates they've derived for the density and velocity.
So it's like making sure that the artificial friction that we introduced actually disappears gracefully
Mm-hmm.
as we approach the true solution.
Precisely, yeah. And they also have to show that the non-local alignment interaction term converges to the correct form in the limit.
Right.
So this involves using the properties of the binary tensor Young measure and carefully analyzing the behavior of this singular kernel that's associated with the fractional Laplacian operator.
It's all about making sure that that limiting solution
Right.
still captures the essential features of the system, like those, interactions between different parts of the swarm.
Exactly. So then they go on to show that the energy inequality holds in the limit, which, follows from the lower semi-continuity
Right.
of the energy functional. And they also demonstrate that the compatibility condition and the support constraints are satisfied by the limiting solution.
So they're ticking all the boxes, making sure that this limiting solution really does satisfy all the conditions we laid out earlier for a dissipative measure-valued solution.
Precisely, yeah. And with that, they've proven their convergence result, showing that a sequence of solutions to these density-dependent viscosity equations converge to a dissipative measure-valued solution of the original Euler alignment system.
It's really beautiful how they're able to use all this mathematical rigor and ingenuity to build these bridges between these different levels of description and shed light on the behavior of such complex systems.
Absolutely. And, I think it opens up a lot of new and exciting avenues for research, inviting us to explore other types of approximations and to delve deeper into the, the properties and implications of these measure-valued solutions.
It's a testament to the power of mathematics to really reveal the hidden order and beauty in this seemingly chaotic world around us. And it's a reminder that even in the face of complexity, there's always more to learn, more connections to uncover, and more mysteries to unravel.
Indeed. The exploration never truly ends.
Well, we've certainly covered a lot of ground today. We've journeyed through the intricate world of these dissipative measure-valued solutions, explored the weak-strong uniqueness principle, and witnessed the elegant convergence of these density-dependent viscosity approximations.
Yeah, it's been a really thrilling ride
Yeah.
through the mathematical landscape.
Absolutely.
Yeah.
And it makes you appreciate the incredible power of mathematics to really illuminate even the most complex and subtle phenomena, like the mesmerizing dance of a swarm.
Absolutely.
Well, I think on that note, we'll wrap up this deep dive.
Sounds good.
Thank you so much for joining
My
us on this
pleasure.
mathematical adventure.
My pleasure.
Until next time, stay curious. Welcome to another deep dive. Today we're going to be looking at the Euler alignment system.
Yes.
And I know you've been particularly fascinated with this idea of proof
Oh, yeah. Definitely.
in this particular paper, and I've seen some of your notes about how elegant some of these proofs are.
Very much so.
So we're going to really try to dive into the concept of proof in this one. And but before we do that, we should probably set the stage.
Sure.
The Euler alignment system, can be used to model things like bird flocks and fish schools and how they kind of move as one.
Yeah, it's all about collective behavior.
So what are some of the building blocks that make up this model?
Well, so at its core, you have two main variables, density, which is represented by the Greek letter, and velocity, which is ia.
Okay.
And density, it's just like how packed the individuals are in a particular space, right?
Right. So if you think of a flock of birds, it's like how many birds are in a cubic meter of space or something like that.
Exactly. Yeah, and velocity, that's just, their direction and speed.
Okay. And the system is governed by a set of partial differential equations that describe how these density and velocity fields change over time.
Okay, so it's not just, the position of the birds, it's also how that position is changing as they move.
Yeah, it's the dynamics of the system.
No, these birds aren't just randomly flitting about, they're
Right.
influencing each other.
Of course.
There's something that's kind of keeping them together. What?
Yeah, so to capture that,
What is that?
we introduced a couple of other terms to the model.
Okay.
So first, there's a pressure term, P of bay.
Okay.
And This basically represents the idea that individuals tend to spread out if they get too crowded.
Okay, so it's like if those birds are getting too close for comfort,
Exactly.
they want to kind of move apart a little bit.
Right. It's like a repulsive force.
Yeah, it makes perfect sense.
Yeah. And then the real magic of the Euler alignment system lies in the inclusion of this alignment term.
Okay, and that's what really keeps them kind of moving as one. Exactly, and this is where the fractional Laplacian operator comes in.
Okay, I've heard of a Laplacian operator.
Yeah.
What's a fractional one?
So it's represented by L with a subscript lambda lu, and it essentially describes this tendency for individuals to align their velocities with their neighbors.
Okay, so, it's like all the birds in a flock are trying to match each other's speed and direction.
Yeah, and it acts like a smoothing force on the velocity field.
So it's almost like they're looking at the birds around them and kind of adjusting their own flight path based on what they see.
Precisely, yeah, they're reacting to their neighbors.
Now, this fractional Laplacian,
Yeah.
I'm assuming it's a bit more complicated than just a regular Laplacian. What makes it fractional?
Right, so unlike a regular Laplacian, this one's non-local,
Okay.
meaning that it takes into account information from a neighborhood around each point, not just at the point itself.
Oh, I see.
So each individual's is influenced by others, not just those immediately next to them, but also those a bit further away.
So it's not just keeping up with the Joneses next door. It's like the
Right.
whole neighborhood is...
It's a whole flock affecting this.
Yeah, it's a more global influence.
Okay, that's really interesting.
Yeah, and the fractional part that comes from the fact that it involves fractional derivatives.
Okay, I'm guessing that's a whole other can of worms we probably shouldn't get into right now.
We could do a whole deep dive on just that.
Yeah, we probably could. But it's suffice to say that it provides a more nuanced way to describe those long-range interactions.
Exactly. It captures those subtleties really well.
Now we've got these equations that describe this system.
Right.
And, they involve these pretty complex operators like the fractional Laplacian.
Yeah, and the pressure term and the nonlinear interactions, they all add to the challenge.
So it sounds like finding solutions to these equations.
Yeah.
It's not a walk in the park.
Might not be so simple.
Yeah.
Are there cases where the standard methods for finding solutions just don't cut it?
Yeah, that's exactly right.
Why is that?
Well, the nonlinearity and non-locality introduced by the alignment term, they can sometimes cause problems for those traditional methods that rely on finding smooth classical solutions.
Okay, so we might encounter solutions that are not smooth. They might have like jumps or discontinuities.
Yeah, exactly, like shocks or oscillations.
That's something.
Right, and those traditional methods, they kind of break down when you have those kinds of behaviors.
So it's almost like the traditional methods are assuming that the solution is going to be like a nice smooth curve.
Right, they're looking for those well-behaved solutions.
But in reality, it might be a lot more jagged and messy.
Yeah, the real world is rarely that simple.
And so that's where these dissipative measure-valued solutions.
Exactly. They provide a more robust framework that allows us to handle those more complex solutions.
So it's almost like we need to expand our toolbox.
Right, we need new tools for a new kind of problem.
To deal with these more difficult solutions.
Yeah.
Now, I know we're going to be talking about measure-valued solutions in detail, but can you just give me a quick high-level overview of what they are?
Sure. So instead of trying to find a precise value for density and velocity at every single point in space and time,
Okay.
we kind of shift to a probabilistic viewpoint.
Oh, interesting.
So we acknowledge that there's some inherent uncertainty in the system.
Okay.
And instead of trying to pin down those exact values, we describe the distribution of possibilities.
So instead of saying, the density at this point is exactly this number,
Right.
we're saying there's a certain probability that it's this number.
Exactly. We're talking about probabilities rather than exact values.
And a certain probability that it's some other number.
Yeah, we're looking at the whole range of possibilities.
So it's almost like instead of looking at a single snapshot,
Mm-hmm.
we're looking at
Yeah.
a range of possibilities across all these snapshots.
Exactly. We're embracing the uncertainty.
And how do we represent this range of possibilities?
So we use a mathematical object called a Young measure, denoted by the Greek letter.
Okay.
And for each point in time and space, gives us a probability measure over the set of possible densities and velocities.
So it's like a snapshot of the system's potential at a particular moment.
Yeah, it tells us what could be happening and how likely each possibility is.
And that allows us to deal with those jumps and oscillations.
Exactly, those discontinuities that would cause problems for those classical methods.
Now, and I know the paper goes into a lot of detail about these dissipative measure-valued solutions.
Yeah, it's a very rigorous definition.
Can you maybe break down some of the key elements of that definition in a way that's a little bit easier to digest?
Sure. So the definition, it's basically laying out the rules for what qualifies as a dissipative measure-valued solution.
Okay.
It's like a checklist of properties that these solutions need to satisfy.
Okay, so what are some of the items on this checklist?
So first of all, the Young measure, it has to be L-bounded.
L-bounded.
Okay. And this basically means that the expected values of density and kinetic energy, they have to remain finite over time.
So it's like setting some reasonable limits on the system's behavior.
Yeah, it's a sanity check to make sure things don't blow up to infinity.
So, the solution can't just have the birds flying off to infinity in all directions.
Exactly. It has to stay within some reasonable bounds.
Okay, so that's L-gray bounded. What else is on the list?
Then there's this concept of a dissipation defect.
Dissipation defect, okay.
It's denoted by D, and it's a function of time that has to be non-negative.
Okay.
And this defect, it accounts for potential energy loss or irregularities in the system.
So it's like acknowledging that the system might not be perfectly efficient.
Right, it's like a fudge factor.
Okay, so it's like in reality, there might be some energy loss due to friction or other things that the model doesn't perfectly capture.
Exactly, it's a way to account for those imperfections.
So L-gray bounded dissipation defect.
And then there are the equations that these solutions need to satisfy. And these are modifications of the classical continuity equation and momentum equation adapted to incorporate the Young measure and the dissipation defect.
So we're taking those fundamental equations of fluid dynamics
Right.
and tweaking them to work in this new framework.
Exactly.
Can you walk us through those modified equations and explain how they differ from their classical counterparts?
Sure. So let's start with the continuity equation.
Okay.
In its classical form, it expresses the principle of conservation of mass.
Which means that mass can't just appear or disappear. It has to move from one place to another.
Exactly. And in the context of measure-valued solutions, this continuity equation, it's modified to incorporate the Young measure.
So instead of dealing with a single value for density, we're now dealing with a distribution of possible densities.
Right. We're working with averages over those possibilities.
Okay, and how does that change the equation?
So the modified continuity equation includes an additional term RC, which represents a potential concentration of mass.
Concentration of mass.
But this measure, it's controlled by the dissipation defect. Okay. Meaning that any concentration of mass has to be accompanied by some energy dissipation.
So you can't just have mass bunching up in one spot without some energy being lost in the process.
Exactly. It's another way to keep the solutions physically plausible.
Now, what about the momentum equation?
So the momentum equation...
That's the one that describes how forces act on the system, right?
Yeah, it describes the change in momentum over time.
Okay. And how is it modified from measure-valued solutions?
Well, in this context, it undergoes a pretty significant transformation.
Okay.
It still captures the idea of momentum balance, but it does so in a way that involves the Young measure and the dissipation defect.
So how exactly does it incorporate the Young measure?
So one of the key changes is the appearance of the binary tensor Young measure.
Binary tensor Young measure. Okay, that's...
It's denoted as HU
Right.
with subscripts Tx and Y, his Txy.
Okay.
And this measure, it captures the correlation between densities and velocities at different points in space.
So it's not just looking at what's happening at a single point.
Right. It's looking at relationships between points.
It's looking at how points are interacting with each other.
Exactly. It's about those interactions.
And why is that important?
Because in the Euler alignment system, those interactions are crucial.
Right. The birds are influencing each other.
Exactly. Their movements are correlated.
So this binary tensor Young measure helps us capture that correlation.
Precisely.
Okay. Now, I also see a term RMM in the modified momentum equation.
Right?
Is that similar to the RC term we saw in the continuity equation?
Yeah, it's very similar.
So it represents a potential concentration of momentum.
Exactly.
And again, it's controlled by the dissipation defect.
Right.
So momentum can't just concentrate without some energy being lost.
It's another way to enforce that physical plausibility.
Okay.
Now, the definition also includes an energy inequality,
Okay.
which basically says that the total energy of the system can't increase over time.
So energy can be conserved or lost, but it can't just magically appear out of nowhere.
Exactly.
Yep.
And this inequality, it explicitly incorporates the dissipation defect.
Okay, so it's like another layer of control on the system's behavior.
Right.
Now, there's one more piece of the definition we haven't discussed yet.
Yeah.
The compatibility conditions.
Right.
What are those all about?
So the compatibility conditions, they're essentially constraints that ensure that these measure-valued solutions interact properly with smooth functions.
Okay.
They provide a link between the abstract world of measures
Okay.
and the more familiar world of functions.
So it's almost like we're making sure that these measure-valued solutions don't completely detach from reality.
Exactly. They have to stay grounded in the physical principles we're trying to model.
And why is that important?
Well, because ultimately we want these solutions to be meaningful and relevant to the real world.
Right, we're not just doing this for abstract mathematical fun.
Although it is fun.
Well, yeah, of course. But we want it to actually tell us something about the world. So those compatibility conditions help us make sure that the solutions are actually physically plausible.
Right. They're a way to enforce those physical constraints.
Okay.
Now, I know this definition can seem pretty daunting at first glance.
It's a lot to take in.
Yeah, it's a lot of technical details.
But it's really a testament to the power of mathematics.
Oh, absolutely.
To be able to construct this framework that's both flexible enough to handle these complex solutions
Right.
and rigorous enough to maintain mathematical consistency.
Yes.
It's really quite impressive.
It is. It's a beautiful piece of mathematical machinery.
Well, I think we've laid a really solid foundation here, exploring the motivation behind the Euler alignment system and delving into the intricacies of these dissipative measure-valued solutions.
Yeah, I think we're ready to tackle those theorems now.
And that's exactly what we're going to do next. But I think we should take a little break. First, let all this information sink in.
Yeah, a breather would be good.
And then we'll come back and really dive into the heart of this research.
Sounds like a plan.
All right, we'll be back in a bit.
See you soon.
Okay, so we're back and ready to dive into those theorems.
I'm excited to see how this all comes together.
Me too. Let's start with theorem 2.1,
Sure.
which, if I remember correctly, deals with how you actually construct these measure-valued solutions.
Exactly. That's what this theorem is all about. It gives us a way to build these solutions.
So instead of just sort of, postulating that they exist,
Right.
this theorem shows us how to make them.
Yeah, it's like a recipe.
Okay, so what's the recipe?
Well, it says that if we have a sequence of approximate solutions
Okay.
to the Euler alignment system.
So solutions that are, close but not quite perfect.
Yeah, they're like rough drafts.
Okay.
And if these solutions meet certain conditions, then they will converge to a measure-valued solution.
So as we refine these approximate solutions, they get closer and closer to a true measure-valued solution.
Exactly. They approach the real deal.
Okay.
And that measure-valued solution will satisfy all those conditions we talked about before.
The whole checklist.
The whole checklist, L found dissipation defect.
Okay, so it's like, if you're sculpting a statue,
Right.
you start with a rough block of stone,
Exactly.
and then you chip away at it bit by bit until you get to the final masterpiece.
And in this case, those approximate solutions, they're like those rough chunks of stone.
Right, and the measure-valued solution is the final product.
Yeah, that's a great analogy.
Now, you mentioned certain conditions that need to be met.
Yeah.
For these approximate solutions to converge, what are those conditions?
So one crucial condition is that the densities of those approximate solutions,
Okay.
they have to be bounded away from zero.
Bounded away from zero so they can't get arbitrarily small?
Exactly.
Okay, why is that important?
Well, from a mathematical perspective, having this lower bound on the densities, it helps us control the behavior of the solutions.
Okay.
It prevents them from becoming too singular or erratic.
So it's like a safety net.
Yeah, it keeps them from going off the rails.
Making sure that the solutions don't just,
Right.
fly off to infinity or something.
Yeah, it ensures that they stay within some reasonable bounds.
Yeah, the proof of this theorem, it involves a lot of technical details.
Yeah, it's a bit involved.
But can you give us a sense of the main strategy?
Sure. So the key idea is to show that those approximate solutions, as we refine them, they get closer and closer to satisfying all the conditions of a measure-valued solution.
So it's like we're checking off those items on the checklist one by one.
Exactly.
And eventually we get to a point where all the boxes are ticked.
Right, and that's when we know we have a true measure-valued solution.
Okay, so that's theorem 2.1.
Yeah, that's the gist of it.
It's a pretty powerful result showing us how to construct these measure-valued solutions.
Yeah, it lays the foundation for everything that follows.
Now let's move on to theorem 2.2.
Okay.
Which introduces this idea of weak, strong uniqueness.
Right, one of my favorite concepts.
And before we dive into the theorem itself, can you just remind us what weak, strong uniqueness means?
Sure. So it's essentially a principle that connects two types of solutions.
Okay.
Weak solutions and strong solutions.
Now, weak solutions, those are the more general ones, right?
Yeah, they're the ones that can handle those discontinuities and oscillations.
Okay. And strong solutions, those are the smooth, classical solutions.
Exactly, those well-behaved ones.
So weak, strong uniqueness is saying that there's a relationship between these two.
Precisely, it's a bridge between those two worlds.
Okay.
And what Theorem 2.2 states is that if we have both a dissipative measure-valued solution...
Okay. One of those weak solutions.
Right.
And a classical smooth solution.
One of those strong solutions.
And they both start from the same initial conditions.
Yeah, they begin at the same point.
Then they will remain identical as long as that smooth solution exists.
So they travel the same path.
So it's like they're two hikers.
Okay.
Setting off on the same trail. One hiker might take a more rugged path.
Yeah, the weak solution.
While the other sticks to the well-maintained trail.
The smooth solution.
But as long as that well-maintained trail exists,
right,
they'll both end up at the same destination.
Exactly. That's a perfect analogy.
Now, why is this principle so important? Why do we care about weak, strong uniqueness?
Well, it tells us that those smooth solutions, those classical solutions, when they exist, they're not just special cases. They're actually embedded within this broader framework of measure-valued solutions.
So it's like those smooth solutions are part of a larger family.
Right. They're not just off doing their own thing.
They're connected to these more general solutions.
Exactly.
And that connection is important because...
well, it allows us to use the tools and techniques that we've developed for those classical solutions to understand the measure-valued solutions.
So it's almost like a Rosetta Stone.
Yeah, it's a way to translate between those two worlds.
That helps us decipher this more complex landscape. Now, you mentioned that this weak, strong uniqueness holds as long as the smooth solution exists.
Yeah.
What happens if that smooth solution breaks down?
That's a great question. And it highlights the power of these measure-valued solutions.
Okay.
Even if the smooth solution breaks down, the measure-valued solution can continue to exist.
So it's like a backup plan.
Yeah, it's a safety net.
All right.
It allows us to analyze the system beyond the point where those classical methods fail.
So it's almost like those measure-valued solutions, they're the adventurers.
Right.
They're the ones who are willing to go off the beaten path.
They're the explorer.
And explore those uncharted territories.
Yeah, they're not afraid of the unknown.
Now, the proof of this weak, strong uniqueness principle.
Yeah.
I know you're really excited about it.
I am. It's a beautiful piece of work.
Can you give us a sense of what makes this proof so special?
Sure. So at the heart of the proof lies this carefully constructed relative energy functional. And this functional, it acts as a measure of the difference between the measure-valued solution and the smooth solution.
So it's like a yardstick.
Exactly.
For how far apart those two solutions are.
Precisely.
And the proof involves analyzing how this relative energy changes over time.
Yeah, we look at its time derivative.
Okay.
And we use the continuity equation and the momentum equation.
That's fundamental equations.
Those are our tools to manipulate and control this time derivative.
So we're using the equations of the system to analyze the difference between these two types of solutions.
Exactly.
And ultimately, the goal is to show that this relative energy, it stays small over time.
We want to keep it bounded.
Okay, so that those two solutions, they stay close to each other.
We want them to travel together.
Now, I know this proof involves a lot of technical details.
Oh, yeah, it's quite intricate.
And clever manipulations.
Yeah.
But is there a particular moment in the proof that you find particularly insightful or elegant?
Well, there are several moments that stand out, but one that I find particularly satisfying is when we realize that we can bound certain terms involving the difference in densities between the two solutions by their relative energy itself.
So it's like we're connecting those density differences back to the overall difference between the solutions.
We're closing the loop.
It's like a feedback mechanism that helps us control the growth of that difference.
Yeah, it's a key step in the argument.
Now, the proof also makes use of some powerful mathematical tools.
Oh, yeah. We bring out the big guns.
Like Gronwall's lemma.
Gronwall's lemma is a classic.
Can you tell us a bit about Gronwall's lemma and how it's used in this proof?
Sure. So Gronwall's lemma, it's essentially a way to control the growth of functions over time.
Okay.
And in this proof, we use it to show that the relative energy, it can't grow too fast.
Okay, so it's like putting a speed limit.
Yeah, a mathematical speed limit.
On how those two solutions can drift apart. And that's crucial for proving weak, strong uniqueness.
Absolutely.
Because if that relative energy grew too quickly, then those two solutions could diverge.
They could go their separate ways.
And we wouldn't have that uniqueness anymore.
Exactly.
So Gronwall's lemma,
yeah,
it's like the anchor that keeps those solutions tied together.
It's the glue that holds the proof together.
Okay, that's a great way to put it.
Now, the proof, as you said, it's pretty intricate.
It is.
It involves a lot of careful manipulations.
Yeah. But it's also very elegant.
Oh,
The
absolutely.
way it all comes together is really impressive.
It's a testament to the power and beauty of mathematics.
Yeah, it's one of those proofs that you read and you're just like, wow.
I know, I get chills every time I go through it.
Me too. It's like a work of art.
It is. It's a masterpiece.
So I think we've covered those two theorems in pretty good detail.
Yeah, we've laid the groundwork.
And now I think we're ready to tackle the main event.
The proof of weak, strong uniqueness.
Yeah, that's what we've been building up to.
I'm ready to unveil the magic.
Me too. Let's take a short break to gather our thoughts.
Yeah, we'll need all our focus for this one.
And then we'll come back and dive into the proof.
I can't wait.
Okay, we're back, and we're finally ready to dive into the proof of weak, strong uniqueness.
The moment we've all been waiting for.
I know. I'm excited to see how all these pieces we've been talking about fit together.
Yeah, it's really a beautiful construction.
So where do we even begin with a proof like this?
Well, as I mentioned earlier, the heart of the proof lies in this relative energy functional.
Right, that mathematical yardstick we were talking about.
Exactly. And it's denoted as EMV, SURU.
Okay, and just to remind us, what do those symbols represent?
So S and U, those are the density and velocity of the measure-valued solution.
Okay.
And R and U, those are the density and velocity of the smooth solution.
Right, so this functional, it's comparing those two solutions.
Yeah, it's measuring how different they are.
And what are the ingredients that go into this functional?
So it has three main components. The first one quantifies the difference in their kinetic energies.
Kinetic energy, so that's the energy associated with motion.
Exactly.
And how do we represent that mathematically?
So it's given by this integral.
Okay.
It's the integral over the domain of the Young measure.
Okay. Right, that's the Young measure associated with the measure-valued solution.
Exactly.
At a particular point in time and space.
And we integrate against the square of the difference between the velocities.
Okay, so it's like we're taking the difference between the velocities of the two solutions,
Right.
squaring it.
To make sure it's positive.
Yeah, and then averaging that over all possible velocities.
Exactly. We're using the Young measure to do that averaging.
Okay, that makes sense.
The second component, it focuses on the potential energy associated with pressure.
Okay, so that's the energy that comes from things being compressed or expanded.
Precisely.
And how does this term capture that?
So this one's a bit more complicated.
Okay.
It involves the pressure function, P, evaluated at both densities S and R.
Right, so we're comparing the pressures of the two solutions.
Yeah, and then we subtract a linear term.
A linear term.
Yeah, a P prime of R times the difference between the densities.
Okay. And why do we subtract that linear term?
It's a technical detail, but essentially it helps us control the behavior of this term.
Okay, so it's like a correction factor.
Yeah, you can think of it that way.
And then we integrate this whole expression against the Young measure.
Right, we average over all possible densities.
Okay, so that's the pressure term. What about the third component?
So the third component, it directly compares the densities of the two solutions.
Okay.
It's basically the integral of the square of the difference between the average density from the Young measure and the density of the smooth solution.
So it's a very direct comparison of how crowded things are in each solution.
Exactly.
Okay, so we've got these three components, kinetic energy, pressure, and density.
Right.
And they all contribute to this relative energy functional.
And by combining them, we get this comprehensive measure of how different those two solutions are.
Now, the proof doesn't just stop at defining this relative energy.
Oh, no, we're just getting started.
Right, we need to see how this difference evolves over time.
Exactly. So the next step is to analyze the time derivative of this relative energy functional.
Okay, so we're looking at how quickly this difference is changing.
Precisely.
And how do we do that?
Well, this is where those fundamental equations of fluid dynamics come in.
The continuity equation and the momentum equation.
Exactly. We leverage those equations to express this time derivative in a form that we can work with.
Okay, so we're taking those equations and using them to analyze the relative energy.
Right. We're connecting the dynamics of the system to this measure of difference.
And you mentioned that we use a modified version of the momentum equation.
Oh, yeah. We have to adapt it to work with measure-valued solutions.
Can you remind us what that modified equation looks like?
Sure. So it involves the Young measure and the binary tensor Young measure.
Okay, those probabilistic ingredients.
Exactly. And it takes this form.
Okay.
We have the time derivative of the average momentum plus the divergence of the average momentum flux plus the gradient of the pressure plus this integral term that captures the alignment interaction.
So it's still capturing those same physical processes.
Yeah, the underlying physics is the same.
But we're expressing it in a way that incorporates those probabilistic elements.
Precisely.
Okay, and this modified momentum equation, it plays a key role in the proof.
Oh, absolutely. It's one of our main tools.
This equation looks pretty intimidating.
It can be a bit daunting.
I imagine it's not easy to work with. It takes some finesse.
So how do we even begin to analyze this time derivative?
Well, we start by using the continuity equation
Okay.
to cleverly rearrange terms within the expression for the time derivative of the relative energy.
So it's like we're doing some strategic algebraic manipulations.
Exactly. We're setting things up in a way that makes them easier to control. And what's the goal of this rearrangement?
The goal is to bound the time derivative by terms that we can manage.
Okay, so we're trying to put some limits on how quickly that relative energy can change.
Precisely. We want to keep it under control.
Now, I remember you mentioned those compatibility conditions.
Ah, yes, those are crucial.
How do they come into play in this part of the proof?
Well, they allow us to estimate certain troublesome terms that arise from the momentum equation.
Okay, so they help us tame those unruly terms.
Exactly. They keep things from getting out of hand.
Can you give us an example of how that works?
Sure. So one key application involves estimating terms that involve the difference in velocities between the two solutions.
Okay.
And using those compatibility conditions, we can relate those velocity differences to density differences.
So we're connecting those two quantities.
Right.
And why is that helpful?
Because it allows us to exploit the structure of the relative energy functional,
Okay.
which involves those density differences.
Right, so we're kind of bringing everything back to that relative energy.
Exactly. We're closing the loop.
Now, as we're going through this proof, are there any particular moments where things start to click, where you see a clever trick or a surprising connection?
Oh, yeah. There are definitely those aha moments.
Can you share one of those with us?
Sure. So one really nice moment is when we realize we can bound certain terms involving those density differences by the relative energy itself.
So it's a self-referential bound.
Yeah, exactly. It's like the relative energy is controlling itself.
And that helps us control the growth of the relative energy.
Precisely. It creates this beautiful feedback loop.
Okay, so we're using the compatibility conditions. We're connecting velocity differences to density differences.
Right.
And then we're bounding everything in terms of the relative energy.
Yeah, it's all coming together.
Now, I know the proof also relies on some clever use of inequalities.
Oh, yeah. Inequalities are our bread and butter.
Can you give us a sense of how they're used here?
Sure. So we use inequalities stemming from the pressure term, and also inequalities that exploit the smoothing properties of that fractional Laplacian operator.
Right, that operator that's responsible for the alignment interaction.
Exactly.
And these inequalities, they help us prevent various terms from blowing up.
Yeah, they keep everything in check.
Can you give us an example of one of those inequalities?
Sure. So one inequality related to the pressure term is it involves the absolute value of the difference between the pressure evaluated at the two densities minus a linear term involving the derivative of the pressure. And this whole expression can be bounded by a combination of terms involving the square of the density difference and a higher power of the density difference.
Okay, and that higher power, it's determined by the properties of the pressure function.
Exactly.
And this inequality, it helps us connect those pressure differences back to those density differences.
Right, which we can then relate to the relative energy.
So it's all about making those connections.
Exactly. It's about building this chain of inequalities.
And we also use inequalities related to the fractional Laplacian.
Oh, yeah, those are essential for controlling terms involving those velocity differences.
Right, because the fractional Laplacian, it has a smoothing effect.
Exactly.
And so the inequalities that capture this smoothing effect, they help us tame those velocity terms.
Precisely.
Okay, so we've got these inequalities that are helping us keep everything under control. But how do we actually bring this proof home? How do we get to the final result?
That's where Gronwall's lemma comes in.
Gronwall's lemma, the grand finale.
The showstopper.
So how does Gronwall's lemma fit into all of this?
Well, first we have to do some groundwork.
Oh.
We have to carefully arrange the relative energy inequality
That's right.
into a form that Gronwall's lemma can handle.
So it's like we're setting the stage for Gronwall's lemma to make its grand entrance.
Exactly. We're laying out the red carpet.
And what does this stage setting involve?
Well, the key is to show that the time derivative of the relative energy can be bounded by a combination of the relative energy itself and the dissipation defect.
So it's like the rate of change of that difference is controlled by the difference itself.
Exactly. It's like a self-regulating mechanism.
And the dissipation defect.
Right. That accounts for any potential energy loss.
Okay, so we've got this inequality that's bounding the time derivative of the relative energy.
Yeah.
And that's where Gronwall's lemma steps in.
Exactly. Gronwall's lemma, it tells us that if the derivative of a function is bounded in this way, then the function itself can't grow too fast.
So in our case, it's saying that the relative energy,
Right.
it can't just explode.
It has to stay within certain bounds.
Okay, and that's exactly what we need to prove weak, strong uniqueness.
Precisely.
Because if that relative energy were allowed to grow without bound,
Right.
then those two solutions could drift apart,
They can become completely different.
and we wouldn't have that uniqueness anymore.
Exactly.
So Gronwall's lemma, it's like the final nail in the coffin.
It seals the deal.
It guarantees that those two solutions stay close to each other.
As long as that smooth solution exists.
Right, that's the key caveat.
Yeah, if the smooth solution breaks down,
Then all bets are off.
then we're in uncharted territory.
But as long as it behaves nicely,
Yeah,
weak, strong uniqueness holds.
exactly.
Well, this has been an incredible journey.
I've really enjoyed it.
Me too. It's amazing to see how all these different pieces come together.
Yeah, it's a beautiful example of mathematical reasoning.
We've got these abstract, measure-valued solutions.
Right.
And these concrete, smooth solutions.
Yeah.
And this proof shows us that they're actually connected.
They're part of the same family.
It's a testament to the power of mathematics to unify seemingly disparate concepts.
Absolutely.
And it's also a reminder that there's always more to explore.
Oh, yeah, we've just scratched the surface.
There's so many open questions and exciting avenues for future research.
The journey of mathematical discovery never ends.
Well, on that note, I think we'll wrap up this deep dive into the Euler alignment system and the fascinating world of measure-valued solutions.
Thanks for having me.
It's been a pleasure having you, and thanks to all of you for joining us on this mathematical adventure. We hope you've enjoyed it as much as we have, and we'll see you next time.
Hey everyone, and welcome back for another deep dive.
Glad to be here.
Today we're going to be taking a look at
Yes.
dissipative, measure-valued solutions and weak, strong uniqueness for the Euler alignment system.
Okay.
This is quite a paper, so we've got an expert here with us today.
Yeah, happy to be here.
So
It's a good one.
this paper really tackles
Oh,
the Euler alignment system,
that's right.
which is a model that's used to understand how groups of individuals, like
Yes.
flocks of birds or schools of fish,
Right.
move and interact.
Yeah, how those individual actions result in
Exactly.
the coordinated group movements
Right,
that
yeah.
we see in nature.
And so let's jump right into the
Uh,
equations in this paper.
Okay.
Equation 1.1
All right.
describes the evolution of this system,
Mm-hmm.
and it seems a bit intimidating at first.
It can be. Yeah.
But really, it captures these key elements so well.
Yeah, it's elegant.
Like density, which is represented by...
Right, representing how closely packed the individuals are, and velocity, which is indicating their
Yeah.
speed and direction.
Okay, so then there's this pressure term, P,
Yes.
which is modeled as P.
Right.
So is that essentially saying that
Yeah.
as the density increases, so does the pressure kind of pushing the individuals apart,
Precisely.
like a crowded room?
Yes, think of it like a crowded room. As more people come in, you
Yeah.
feel more pressure to move away from those denser areas,
Right.
and Peru controls how sensitive that pressure is to the changes in density.
Okay, that makes sense.
Yeah.
So now we get to the star of the show.
Yeah.
This commutator term, LU,
All right.
in equation 1.2.
Okay.
And this is where the alignment behavior
Yeah, this is
really comes in.
where it's at.
Right.
Yeah.
So the commutator,
Yeah.
how individuals adjust their velocities based on the movement of others around them.
Yeah. That's right. It's the mathematical representation of that swarm intelligence
Yeah.
that allows for that
Okay.
synchronized movement.
So this commutator involves this fractional Laplacian, LU,
Right.
which is defined with a singular kernel
Yeah, in 1.2.
and 1.2.
Yep.
So can you break that down for us a little bit?
Yeah, so the Laplacian in general kind of measures
Okay.
how much a function is changing at a given point.
Uh-huh.
So think of it like it's detecting the bumps and curves in the function.
Okay.
The fractional Laplacian is,
Okay.
it's a little more nuanced. It's kind of like a softer version of the standard Laplacian,
Okay.
but it still captures some of those smoothing effects.
So in this system, is it kind of acting like a
Right. It's like,
stabilizing force?
yeah, it's like adding a bit of mathematical friction to
Okay,
the system,
got it.
which plays a role in that dissipative
Mhm.
nature of the Euler alignment system.
Okay. Fascinating.
Yeah.
The paper also mentions this fractal Burger's equation 1.3
Right.
as a simplified case when Rex 1.
Right, when the density is constant.
Okay, so what's the significance of that connection?
Yeah. Well, the Burger's equation is a well-known model
Okay.
in fluid dynamics,
Yeah.
and the fractal version of it
Okay.
exhibits some interesting properties related to
Okay.
shock wave formation and turbulence.
Mhm.
So by highlighting this connection, the authors are kind of hinting
Okay,
at the rich mathematical structure
got it.
underlying the Euler alignment system and its potential links to other research areas.
So we've got this complex system with density, velocity, pressure,
Yeah.
this alignment mechanism driven by the commutator.
Right.
But this paper focuses on dissipative, measure-valued solutions. So before we get into the specifics of those,
Yeah.
can you tell us why proving global well-posedness for this system
Right.
is so challenging?
Yeah, so global well-posedness means that we want to show that a solution to the system
Okay.
exists for all times,
Yeah.
that it's unique,
Okay.
and that it behaves in a mathematically sensible way.
Right. It doesn't break down
Right, it doesn't give us
or give us nonsense results.
nonsense.
Yeah, as
right,
time goes on.
As time goes on.
Like,
So proving this can be tricky, especially in higher dimensions where the interactions become much more intricate.
higher dimensions meaning like,
Yeah, like birds flying in 3D space
All right.
rather than just on a plane.
got it.
And when you add the pressure term, things get even more challenging.
Yeah.
Previous research has made some progress on simpler cases,
Mm-hmm.
like the pressureless system,
Mm-hmm.
or systems with specific initial conditions.
Okay.
But the general case with pressure in higher dimensions is still
Right.
an open question.
A mathematical mystery.
Yeah,
So this paper is stepping up to that challenge
that's right.
with the concept of measure-valued solution.
Right.
So can you give us an overview of what those are?
Yeah, so traditional solutions to these equations often involve smooth functions, but real-world systems can be messy.
Right.
So that's where measure-valued solutions come in.
Okay.
Instead of describing the system with specific values at each point,
Mm-hmm.
they use probability measures to capture the system's behavior.
Okay.
So think of it as a statistical description.
So instead of saying this bird is at this exact location with this exact speed,
Right.
we're saying,
We're saying there's a certain probability of finding a bird
okay,
with a certain range of speeds in this area.
got it.
Yeah.
Okay, so that's particularly useful
And this is useful,
for systems like this.
particularly for systems like the Euler alignment system.
Okay.
Because it allows us to deal with situations where those nice, smooth functions might
they'd be
break down
Right.
or become too difficult to analyze.
So it's a more flexible and robust
That's right.
approach
Yep.
that can handle those complex.
Potentially messy scenarios.
Yeah.
Now, the paper introduces a specific type of measure-valued solution
Right.
called a dissipative measure-valued solution.
Yes.
What makes these solutions dissipative, and why is that important?
Yeah, so a dissipative system like the one described here
Mhm.
is one where energy is lost over time due to factors like friction or viscosity.
Okay.
So think of a pendulum swinging back and forth.
Yeah.
Eventually, it comes to a stop
Right.
because of air resistance.
So it's like the system is slowly winding down
Exactly.
over time.
Yeah.
And this dissipative nature is captured in this energy inequality
Right.
for the Euler alignment system.
Yeah.
And this inequality states that the total energy of the system at any given time
Right.
is less than or equal to the initial energy,
Mm-hmm.
plus any energy that's been dissipated.
That's right.
So energy can't magically appear out of nowhere.
Exactly.
It either stays the same or decreases over time.
And this energy inequality plays a crucial role in
Right.
proving the existence and stability
Yeah.
of these dissipative measure-valued solutions.
Yeah.
So we've got these dissipative measure-valued solutions,
Okay.
which are a bit like these probabilistic descriptions of the system.
Yeah.
But how do we actually represent these measure-valued solutions mathematically?
Right. Well, that's where
Yeah.
Young measures come in.
Yeah.
They're a powerful mathematical tool for representing these probability measures.
Got it.
Instead of assigning a single value to each point, a Young measure assigns a probability distribution,
Okay.
allowing us to capture the uncertainty and variability
Right.
inherent in the system.
So it's like instead of having a single snapshot, we're getting a whole spectrum of possibility
Exactly.
at each point.
Yeah.
And the paper introduces a specific type of Young measure called a binary tensor Young measure.
Right.
And these are essentially product measures that combine information about two different points in the system. So they're particularly useful for analyzing these non-local interactions.
That's right.
You know, individuals separated by some distance.
Yeah.
So they're capturing how those individuals are influencing each other.
Exactly.
Even when they're not right next to each other.
Yeah, that's right.
And these binary tensor Young measures have special properties.
Some special properties.
Like they're symmetrical.
Yeah, they're symmetrical.
Meaning that they don't care which point you consider first.
That's right.
And they also satisfy this consistency condition.
Yes.
Which ensures that they agree with the original Young measure.
Right.
When you look at a single point instead of a pair.
When you look at a single point instead of a pair. Yeah.
So we've got our system. We've got these dissipative measure-valued solutions.
Yeah.
We've got these binary tensor Young measures to represent them.
Right.
So what's next?
So what's next? Well, now we need to define what a dissipative measure value solution actually looks like in this framework.
Okay.
And the paper lays out all the conditions in definition 2.3.
All right.
It might seem a bit daunting at first.
Okay.
But it's really just a checklist of all the properties that these solutions need to satisfy.
A checklist. I like things organized.
I know, right?
So what are some of the key items on this checklist?
Yeah, so first, of course, we have the Young measure itself, which is that mapping from each point in space and time to a probability measure.
Right.
Then we have this L-boundedness condition, which essentially ensures that the expected values of the density and velocity don't blow up to infinity. It's like saying, yes, we're dealing with probabilities, but those probabilities still need to make sense within the system.
So it's like a way of keeping things mathematically grounded.
That's right.
And making sure that those probabilities don't become nonsensical.
Exactly.
What else is on the list?
So we also have the dissipation defect, denoted by D. This is a non-negative function that captures the energy loss due to the dissipation in the system.
Oh, right. Like how the pendulum eventually loses all its energy to air resistance.
To air resistance. So the dissipation defect is quantifying that energy loss.
So that's the energy part. What about the equations themselves?
Right.
How do those fit into the definition?
Yeah, so the next two items on the list are the equation of continuity and the momentum equation. These are fundamental equations in fluid dynamics that describe how the density and momentum of a fluid evolve over time. In the context of measure-valued solutions, these equations are expressed in terms of the expected values of those quantities, calculated based on those probability measures.
So instead of having precise values at each point, we're working with averages.
We're working with averages.
Based on those.
Based on the probability
distributions, right?
That's right.
And these equations also include some additional terms.
Yes, they do.
RC for continuity. And RM for momentum. And these are measures that account for any potential discrepancies.
Yeah, that's right.
Or defects in the solution.
Think of them like error bars.
Ooh,
in a statistical analysis. Acknowledging that we're dealing with approximations and uncertainties.
So they're helping ensure that the solution is consistent. And meaningful. Even in those messy scenarios.
Even in those messy scenarios.
Where things might not be perfectly smooth or predictable.
Right.
What else is on our checklist?
So we also have the energy inequality, which we've already discussed.
Right.
That's crucial for confirming the dissipative nature of the solution and ensuring that the energy bookkeeping is consistent.
Okay. Energy is accounted for. What's next?
Then there's this compatibility condition. This is a fascinating condition that links the measure-valued solution to smooth solutions.
Got it.
Essentially, it says that if there exists a nice, well-behaved, smooth solution, then the measure-valued solution shouldn't stray too far from it.
So it's like a quality control check, making sure the measure-valued solution doesn't go completely off the rails from a known good solution.
From a known good solution. That's a good way to put it.
And finally, we have a condition on the support of the Young measure.
Yes.
And this condition ensures that the Young measure only assigns positive probability to physically meaningful states. So those with positive densities.
That's right.
We can't have a negative number of birds in a flock.
Exactly.
So this is like a reality check for the probability distributions.
You got it.
Okay, so that's the definition in a nutshell. Seems like a lot,
It is.
but it's a careful and precise way of defining
Right.
what it means for a solution to be a dissipative, measure-valued solution in this framework.
Yep.
Okay, so we've got our concept of a dissipative, measure-valued solution.
Okay.
We've got a way to represent them using Young measures, specifically these binary tensor Young measures.
Right.
So what did the researchers actually achieve with this framework?
All right.
What are the key results of this paper?
There are two major achievements that I think really highlight the power of this approach.
Okay.
The first one is Theorem 2.1. It proves that under certain conditions, solutions to a slightly modified...
Okay, a modified version, did they tweak the equations?
They added a small term that acts like a stronger type of mathematical friction.
Okay.
So this extra term helps smooth out the solutions.
So it's adding a little bit of mathematical grease to the system.
It's a good way to put it.
To make everything flow smoothly.
To a solution.
To a solution, yeah.
So yeah, they tweaked it a little bit just to make it easier to work with.
Okay.
But yeah, and the second key result is Theorem 2.2. Which establishes a weak-strong uniqueness principle.
Okay, weak-strong uniqueness, what does that mean?
So it means that if a smooth solution exists for the Euler alignment system, then it's the only solution within the larger family of dissipative, measure-valued solutions.
So it's like saying if we have a gold standard solution.
Exactly.
That nice, smooth function.
Yeah, a really nice, well-behaved.
That solves the equations.
Yeah.
Then all of our other more general solutions should agree with it.
Exactly.
So we're adding this layer of certainty to this initially very probabilistic, uncertain approach.
So it's a brilliant example of how different mathematical techniques can work together to give us a more complete and robust understanding of a complex system.
So I'm really starting to see the power of this framework.
Yeah.
But those are just the statements of the theorems.
Right.
I'm dying to know how they actually proved these results.
Yes.
What are some of the key techniques and insights?
Yeah, the proofs themselves are quite a journey.
Okay.
But they're really elegant.
Okay.
Maybe we can start by diving into the proof of Theorem 2.1.
Yeah.
That convergence result.
Absolutely. Let's see how they constructed that mathematical bridge from those modified equations to those dissipative measure-valued solutions.
Yeah.
Okay, so let's unpack this proof of Theorem 2.1. Okay. It's all about showing that solutions to those modified Euler alignment equations converge to a dissipative measure-valued solution, right? And the proof utilizes some pretty powerful tools for mathematical analysis. Weak compactness arguments. And Young measure compactness.
All right.
So compactness. Can you refresh our memory on what that means and why it's so important here?
Yeah, so think of compactness as a way of taming infinity.
Okay.
So in this context, we're dealing with sequences of functions that represent the approximate solutions to those modified equations.
Okay.
Compactness tells us that if those sequences are well-behaved, meaning they don't oscillate too wildly or grow too large, then we can extract a subsequence that converges to some limited function.
So even though we have infinitely many functions in the sequence, there's a sense in which they're clustering around some well-defined limit.
Exactly.
And weak compactness means that the convergence might not be perfect at every single point, but it'll converge on average.
Yeah, in a way that's
still meaningful.
Mathematically meaningful?
Mathematically, okay.
Yeah.
So how does this apply to the proof?
So in the proof of Theorem 2.1,
Theorem 2.1,
the authors use weak compactness to show that the sequences of densities and momenta, you know, those grow and break terms we saw in the equations, have subsequences that converge weakly to some limit.
Okay, so we're starting to see those approximate solutions settling down towards something specific.
Towards something specific.
Now, where do Young measures come into play?
So Young measure compactness takes this idea a step further. Remember, we're not just dealing with functions. We're dealing with probability measures. Young measure compactness tells us that if we have a sequence of functions generating those probability measures, and those functions are well behaved in a certain sense, then the corresponding Young measures also converge to some limiting Young measure.
So if the building blocks converge,
Yeah.
then the structure they build
Yeah.
also converges.
It's a brilliant analogy.
Yeah.
Yeah, and this is crucial for the proof
Okay.
because it allows us to show that the Young measures generated by those approximate solutions converge to the Young measure of the desired dissipative measure-valued solution.
So these compactness arguments are like
Yeah, they're the heavy lifters. Yeah.
giving us those crucial
convergence results. Yeah.
But we're dealing with a pretty complex system here.
Yeah.
We've got that pressure term and that non-local interaction term involving the fractional ablation.
Yeah.
So how do those factors
That's right.
come into play in the proof?
So those terms add significant complexity.
Okay.
Let's tackle the pressure term first.
Okay.
The pressure term, EQ, introduces nonlinearity into the equations, making them more challenging to analyze.
Nonlinearity. That sounds like a headache for mathematicians.
It can be.
Yeah.
But the authors handle it skillfully.
Okay.
They use the fact that the pressure function is smooth and grows reasonably fast as the density increases.
Okay.
This allows them to control the pressure term in the equations and ensure that it doesn't cause any wild, uncontrollable behavior in the solutions.
So they're putting bounds.
Exactly. They're putting bounds.
On how crazy the pressure can get.
On how crazy the pressure can get,
Yeah, and they show that these bounds are preserved.
And they show that these bounds are preserved.
As we take the limit.
Meaning the pressure term.
Meaning the pressure term behaves nicely.
Behaves nicely.
In the measure-valued solution as well.
In the measure-valued solution as well, okay.
Yeah.
So the pressure term is under control.
Okay.
What about that non-local interaction term?
With the fractional ablation.
Yeah.
That seems particularly tricky.
Yeah.
Especially with that singular kernel.
You're spot on.
Yeah.
That term is one of the most challenging aspects of the entire proof.
Right.
The fractional ablation with its singular kernel introduces long-range interactions into the system.
Right.
Meaning that individuals can influence each other.
Okay.
Even when they're separated by a significant distance.
So it's like those birds in a flock
can
sense each other's movements.
Yeah.
Even when they're not.
Yeah, even when they're not right next to each other.
Right next to each other.
Yeah.
And to handle this term in the limit.
Right.
The authors use a clever multi-step approach.
A multi-step approach.
They break down the integral involving the fractional ablation into different parts. Each corresponding to different ranges of interaction distances. So they're slicing and dicing that complicated integral to make it more manageable.
That's right.
And they carefully analyze.
The
behavior of each part.
Right.
As that regularization parameter goes to zero. They use the properties of the fractional ablation.
Right.
And the interplay between density and velocity.
Yeah.
To show that each part converges to the desired limit.
That's right. It's like a delicate balancing act.
Right.
Making sure every piece of the puzzle converges correctly.
And how do those binary tensor Young measures come into play here?
Right. So they're crucial for rigorously identifying the limit of that non-local term.
Okay.
Remember those special properties we discussed earlier?
Yeah.
The symmetry and consistency conditions?
Right.
Those properties are essential for proving that those long-range interactions captured by the fractional ablation are handled correctly in the limit.
So the compactness arguments give us the overall convergence.
Yeah.
And those careful manipulations of the pressure term and the non-local term ensure that everything behaves nicely in the limit. But we're still missing a key piece of the puzzle.
Yeah.
That energy inequality, which is so important for confirming the dissipative nature. Of the solution.
Yep.
How do they prove that the energy inequality holds for the measure-valued solution?
So proving the energy inequality is another critical step.
Okay.
And it involves some clever use of weak convergence
Right.
and lower semi-continuity.
Okay.
Properties of certain functionals.
Okay.
It's a bit technical, but the essence is that they show the energy inequality.
Right.
For those regularized approximate solutions carries over to the limit.
So if the energy inequality holds for those nicer solutions.
Yeah, for the nicer solutions.
It should also hold for the limiting measure-valued solution.
Measure-valued solution,
Right.
exactly. And this requires careful analysis of the various energy terms, the kinetic energy associated with the motion,
Okay.
the potential energy due to the pressure,
Right.
and the energy dissipated
Okay.
due to that mathematical friction.
It's like meticulously balancing a budget,
That's a good way to put it.
making sure that no energy is magically created or destroyed.
Created or destroyed in the process.
In the process, yeah.
Yeah.
So we've got the convergence.
Okay.
We've got the energy inequality.
Yeah.
What's left
So what's left?
to wrap up this proof of Theorem 2.1?
Of Theorem 2.1.
Yeah.
The final step is to show that the support of the Young measure,
Okay.
the set of points where it assigns positive probability,
Right.
is restricted to physically meaningful states,
Right.
those with positive density values. This is where that uniform lower bound on density plays a crucial role.
Right. We can't have negative birds.
Exactly. We can't have negative birds.
Yeah.
That lower bound acts as a safety net,
Okay.
preventing the density from collapsing to zero,
Right.
which would lead to nonsensical results.
So that lower bound is a guarantee that our mathematical model stays grounded in physical reality.
Precisely.
And with all these pieces in place, the convergence, the energy inequality, the support of the Young measure, the authors have beautifully demonstrated that those solutions to those modified equations converge to a dissipative measure-valued solution.
It's a testament to the power of careful analysis and deep mathematical tools.
Wow, what a journey.
Yeah.
It's amazing to see how they tackled those challenging pressure and non-local interaction terms.
Yeah, and how that uniform lower bound kept everything physically meaningful.
Physically meaningful, yeah.
Yeah.
Now I'm ready to delve into the proof of Theorem 2.2.
All right.
That weak, strong uniqueness principle.
Yes.
What are the key insights?
So that proof is another gem.
Okay.
And it revolves around this clever concept called the relative energy functional.
Okay.
It's a fascinating way
Right.
to compare a measure-valued solution to a smooth solution and track how close they are in terms of energy.
Okay.
Are you ready to dive into that?
Absolutely. Let's unravel this weak, strong uniqueness principle and see the magic of relative energy in action.
Right.
Okay, so we're diving into the proof of Theorem 2.2.
Right.
This weak, strong uniqueness principle.
Yes.
And you mentioned this intriguing concept of a relative energy functional.
Yeah.
Can you elaborate on what that is?
Absolutely.
And why it's so crucial here?
So the relative energy functional is a powerful tool for comparing two different solutions to a system of equations.
Right.
In this case, we're comparing a measure-valued solution to a smooth solution.
Right. That nice, well-behaved function.
Right. Which we hope exists.
That we hope exists, right?
Yes.
So is it like a way to measure how far apart those two solutions are?
Yes.
But instead of using a ruler, we're using energy as our yardstick.
That's a good way to put it.
So the relative energy functional quantifies the difference in energy between the two solutions.
Between the two solutions.
It takes into account.
Right. It takes into account
The differences in densities, velocities.
Yep.
Even those pressure contributions.
Even pressure. That's right.
It's a comprehensive
measure that captures all the relevant discrepancies.
So it's not just about how fast they're moving.
Right.
Or where they're located.
Yeah.
But also about
how much stuff is present and how squeezed together it is.
Squeezed together, right?
Yeah.
It's a holistic measure.
Yeah, it's a holistic.
Of how much those two solutions deviate.
That's right.
From each other.
Yeah.
And the key insight of this proof is
Yeah.
that if we can show that the relative energy between a measure-valued solution and a smooth solution starts at zero and stays at zero, then those two solutions
They must be the same.
must be the same.
That's right.
So if they start with the same energy
Yes.
and never diverge in terms of energy, they must be the same solution.
They must be the same solutions, like two runners starting at the same point
Right.
and running side by side.
Side by side for the whole race.
But the whole race.
Yeah.
That's the heart of the weak, strong uniqueness
That's right.
principle.
Exactly.
If a smooth solution exists, then any measure-valued solution that starts with the same initial condition
Must remain identical.
must remain identical to that smooth solution.
So that smooth solution.
For all time.
For all time. Okay.
Yeah.
That makes sense.
Yeah.
Intuitively.
Yeah.
But how do we actually show
So how do we show?
that the relative energy stays at zero?
Right.
I'm guessing it involves
Yes, it involves some sophisticated mathematical maneuvering.
Mathematical maneuvering, right?
It's right.
So the proof involves deriving something
Right.
called a relative energy inequality.
Okay.
And this inequality
Yes.
essentially describes how the relative energy changes over time.
That's right. And by carefully analyzing
Okay.
the terms in this inequality,
Uh-huh.
the authors show that under the right conditions,
Okay.
the relative energy cannot increase.
So it's like proving that the energy gap
That's right. The energy gap
between those two solutions
can never widen.
can never widen.
Yeah.
So to derive this inequality,
Right.
the authors combine
Yes, they combine.
the energy inequality
Uh-huh.
for the measure-valued solution
Right.
with the equations satisfied
Right.
by this smooth solution.
It's a delicate dance of manipulating those equations.
Right.
Integrating by parts.
Right.
And cleverly exploiting the properties of
Right.
that fractional Laplacian.
Sounds like a mathematical ballet.
It is. It is.
A lot of precision.
Yeah, a lot of your
Precision and finesse.
Can you give us a glimpse into some of the key steps involved?
So one of the crucial steps is
Right.
carefully estimating the various terms
Right.
that appear in the relative energy inequality.
Okay.
These terms capture the contributions
Okay.
from the differences in densities,
Right.
velocities, pressures,
Mm-hmm.
and even those non-local interactions
Okay.
mediated by the fractional Laplacian.
So it's a comprehensive accounting of all the factors.
Yeah, that's a good way to put it.
That could potentially
Right.
drive those two solutions apart. Yep. Drive those two solutions apart energy-wise.
Energy-wise, and the authors use
And they use
a combination of tools.
A combination of tools.
Properties of the smooth solution.
Yep.
Bounds on the measure-valued solution.
Mhm.
And importantly, that uniform lower bound
And importantly, that uniform lower bound
on the density,
density.
to control those terms.
Right, to control those terms.
And prevent the relative energy
and prevent the relative energy from increasing.
from increasing. That uniform lower bound
I know.
is popping up everywhere.
It is.
It's like the unsung hero
It is. It plays a crucial role
of this entire framework,
in ensuring that the solutions remain well-behaved
right?
and that those energy estimates hold up.
Okay, so we've carefully estimated those terms
All right.
in the relative energy inequality.
Yep.
What's the final move?
So the final touch is applying Gronwall's lemma.
Okay.
It's a powerful tool
Right.
in mathematical analysis
Okay.
that lets us control the growth of a function if we have an inequality involving its derivative.
So if we know how fast something is changing,
Exactly.
you can put limits on
We can put limits
how big it can get.
on how big it can get.
Right.
And in this case,
Okay.
we have an inequality
Right.
for the derivative
Yep.
of the relative energy.
Okay.
So Gronwall's lemma comes to the rescue,
Okay.
allowing us to bound the relative energy over time.
So by carefully estimating those terms
Right.
in the inequality
Yeah.
and then applying Gronwall's lemma,
Yeah.
we can show that the relative energy
Right.
stays bounded.
Stays bounded, never growing too large.
Never growing too large. And since it starts at zero,
And since it starts at zero,
that means it must stay at zero,
it must stay at zero.
proving that those two solutions are the same.
That's the essence of the argument.
It's a beautiful combination
Yeah, it is.
of careful analysis,
It is.
clever manipulation of the equations,
Yep.
and strategic use
Strategic use of that powerful tool.
of that powerful tool, Gronwall's lemma.
Gronwall's lemma, that's right.
Wow, what a journey.
I know it's
It's been amazing to see
a wild ride.
how these researchers constructed this framework
Right.
of dissipative, measure-valued solutions.
Yep.
And then use it to prove
And then use it to prove these remarkable results.
these remarkable results.
Convergence in 2.1.
Convergence in 2.1
And that weak, strong uniqueness
and weak, strong in 2.2.
in 2.2.
It's like they've opened up a whole new way
Yeah, they really have.
of understanding these complex systems.
A whole new way of understanding these complex systems.
And what's particularly exciting is that this research
Yeah,
has implications far beyond
right. Far beyond
the specific
any
model
specific models
that are
And
analyzing
if they're analyzing here,
the tools and techniques
the tools and techniques they've developed
that they've developed.
could be applied to a wide range of other
Right.
systems
Systems that exhibit collective behavior.
that exhibit collective behavior.
Think about traffic flow,
Graphic flow.
crowd dynamics,
Yeah.
the spread of information
Right.
or ideas
Or ideas through social networks.
Through social networks.
All of these systems involve
Right.
individuals interacting
Yeah.
and influencing each other.
And this framework
And this framework
of dissipative measure-valued solutions
measure-valued solutions has the potential to revolutionize the way we model.
the way we model and analyze them.
And analyze them, that's right.
It's like they've given us a new set of lenses
Yeah, it's like a new set of lenses
to view these.
to view these complex systems.
Complex systems revealing hidden patterns and connections.
Revealing hidden patterns and connections
Well, we couldn't see before.
that we couldn't see before.
And the fact that this framework aligns so well
Right?
with the way we often approach these problems numerically through computer simulation
That's right.
makes it even
More.
powerful and relevant.
Yeah.
It's like those measure-valued solutions are
Right.
bridging the gap
Bridging the gap.
between the abstract world
Right.
of theoretical mathematics
All theoretical mathematics.
and the concrete world of real world.
In the concrete world
That's
of
real fun.
real-world applications. Yeah.
I couldn't have said it better myself.
Yeah. And I think this paper is just
Mhm.
the tip of the iceberg.
Yeah.
It's an invitation to explore further,
Yeah.
to push the boundaries of these mathematical tools,
Right.
and discover new insights
Right.
to the fascinating world of collective behavior.
Well, I don't know about you, but my brain is officially full.
As is mine.
In a good way, of course.
In a good way.
It's been an absolute pleasure diving deep
It really has.
into this paper with you.
It's been a joy to share this journey
It has.
with you, and I hope our listeners have enjoyed it as well.
So for those of you who are eager to delve even deeper, we'll be sure to include links to the paper
Absolutely.
and other resources in the show notes.
Yep. And as always,
And as always,
feel free to reach out
reach out
to us with any question
with any questions or thoughts.
that you men have.
Until next time, keep those brains buzzing and keep diving deep into the fascinating world of knowledge.
That's right.